to today's webinar entitled Free Software Tools for Microanalysis 2022. And by microanalysis here, we're referring to X-ray spectrometry using the scanning electron microscope or the electron microprobe. And I wanted to remind everyone that the webinar today is sponsored by the Microanalysis Society, and we encourage you to visit the URL posted on the screen for more information about MAS activities and resources. The co-hosts for today are myself, Edward Vicenzi from the Smithsonian Institution, and Owen Neill from the University of Michigan. So the schedule for today is broken into 6 presentations and a discussion period. And we will try our best to keep to the schedule listed on the screen there. The first presentation will be given by Nicholas Ritchie. He's a microanalyst from the National Institute of Standards and Technology, specializing in particle analysis and standards-based EDS analysis. His PhD from physics in physics from Rice University, and Nicholas is the author of NIST DTSA-II and more recently NEXL libraries for quantitative electron excited X-ray microanalysis in the Julia language. So today he's going to be describing the virtues of DTSA-II, which is a multi-purpose software platform for X-ray microanalysis.
All righty, you ready to go then? I guess it's a few minutes
please.
early. Okay, great. So I will start. Okay, so you have to stop sharing your screen.
Yes, I am doing that right now.
Okay, great. All righty, so thank you very much for this opportunity to talk to you all today and to present this DTSA-II. I look forward to seeing many of you at M&M this year. It's been a while, and it'll be good to see you all. So let's dive right in. As the slide showed that Ed showed earlier, spoke to, that there's really 3 parts of DTSA-II, and I'm going to try and cover all 3 of them in the 40 minutes that I have available to me. The first part is standards-based quantification. Second part is simulation, and then the third part is optimization. And so we're just going to start with the tool that I think a lot of people use this for is standards-based quantification. And so we're going to go along the way and cover various different parts of the software with the hope that what I tell you here today would help you get started with the software if you're interested in doing it. If you're interested in downloading the software, I've made a new update available. It's a few days old at this point, and it's available on the NIST website. Your best bet for finding it is just to Google NIST DTSA-II. So let's get started. Let's take a look at some spectra that were collected on our Joule microprobe. They're from a glass that was engineered here at NIST, and I'm already forgetting what I had to do. So I'm going to actually, I went to try and open the files up, and it's telling me that I'm not using the right detector, which is a good learning experience, maybe. And so I'm going to cancel out of that and actually go and select the correct detector. So detectors are an important part of DTSA-II, and I'm going to talk more about them later. But for the moment, let it just be said that you can select detectors from a list box in the front here of the available ones to you. And I'm going to select the detector on which this particular set of spectra were collected. So how did it know that I had the wrong detector? Well, it looked at the properties of the spectrum and realized that the energy scale was not matching the one that was currently active. So I've got these 15 spectra. As you can see, they overlay each other incredibly well, which speaks to the homogeneity of the sample, and also the fact that these are fairly deep spectra, many counts. So probably the first thing you're going to want to do when you've opened up a set of spectra is try and figure out what are the elements in here. And so, of course, DTSA-II has KLM line built in and a tool for allowing you to scroll through them and identify the various different peaks in the spectrum. So I'm just scrolling through the elements in atomic number order and identifying the peaks. That could be sodium, it isn't. That's aluminum, that's silicon. And this way I can go through and I can identify all the elements in a material. There are other ways you can do this too. So for example, I could just type in the element here and then type Control-Enter. And that would also input the element. I can actually input multiple elements and do the same thing. And it puts all the labels up for those particular elements. So there's shortcuts, and then there's the way you would do it if you don't know what the elements are. Doing your qual up front is probably the most important thing you can do in quantitative analysis, because if you get these elements wrong up front, everything else goes downhill from there. So there's actually one more way I'm just going to show you, and that is you could actually type in the name of the material. And this is dependent upon the fact that this material is actually located in the material database that's associated with DTSA-II. And so we'll speak to a little bit more about that. But the material database is something that you can customize and add your own materials to. So I happen to know that this glass is in the database as this material name. And so I'm just going to do Control-Enter. It goes to the database, finds out what elements are in there, and labels all the peaks. So I can now zoom in a little bit on the spectrum, do all the sorts of spectrum manipulation kinds of things you would want to do. Okay, so that's allows us to take a look at the spectra. I can select one or more, I can select them all. What I'm going to do now is go ahead and quantify this spectrum. So quantifying the spectrum uses one of the tools, one of the primary tools in DTSA-II. And I'm going to select a quantification mode, which is to determine the composition of an unknown spectrum by fitting to standards. So DTSA-II does not support standardless analysis. It's only for standards-based analysis. So we're going to need to provide some standards. And DTSA-II works a lot on this whole idea of these sort of wizard interface, where you step through the process of providing the information that you need, that the software needs. So it's actually extracted a lot of this information already out of the spectrum automatically. The next thing it's going to ask me to do is provide some standards. So I'm actually just going to use a set of spectra for the standards. We're going to talk about this thing called a standard bundle later, but for the moment, we're just going to use spectra. These are just standard EMSA spectra. DTSA-II can read many different formats of spectra, but EMSA is often the best one to use. So, and it's supported by almost all the EDS vendors. So I'm going to pick a set of spectra that I'm going to use for standards. And I'm picking one spectrum for each element. Sometimes spectra can actually be standards for multiple elements. Anyway, I've selected these spectra based on the qual that we've already just performed. And I'm going to, it asks me then for spectra that are ambiguous. So calcium fluoride, it's not clear whether I want to use that as a standard for calcium or fluorine. I'm going to select it for calcium. And all the other spectra, there's no ambiguities. So you can see here that it's loaded in the spectra and actually recorded some information from the spectra. So some of the most important information is actually what the probe current was. So that's this column right here in nanoamps, what the live time is. This information is very important because this provides you with the dose, which is essentially the number of electrons that were impinged on the sample to create the spectrum that we've measured. Okay, so next, it's going to ask us if we want to look for any unmeasured elements. So these are things like element by difference or oxygen by stoichiometry if I hadn't provided a standard for oxygen. It's disabled because I did provide a standard for oxygen. So we're actually going to measure oxygen in this case. Then we're going to specify, we'll talk more about reference spectra, but reference spectra are part of the whole quantification process. There's what we call standards, which provide the intensity information, and then there's reference spectra, which provide the shape information. And often the standards can act as both. So they provide both intensity information and shape information. And in this case, they are capable of doing that. We'll talk a little bit more later when they aren't. The main reason that they wouldn't be is because there is a peak interference, meaning that the standard material has multiple elements in it, and some of those elements have lines that interfere with each other. So they overlap, or they are very close to each other. So in this case, we can see that all the spectra actually have good signal to noise, meaning that there are intense peaks for all of these various different elements. So we can specify explicitly which lines we want to use to quantify. So in EDS, you often have multiple characteristic X-ray peaks that you can use to perform the quantification. For example, germanium has peaks at low energies, an L line, and then at around 10 and 11 kV, a pair of K lines. So I'm actually just going to let DTSA-II automatically pick which lines to use. If you want to force it, you can also do that just by highlighting, clicking on one of these and selecting the line you want to use. We're going to go through all 15 spectra and quantify them like that. And we end up with a table of results. Actually, you know what I'm going to go? I'm going to skip back and pick these other ones, and let's see if we can go. Okay, this ended up being slightly better. In this case, I think what it did was it took the germanium differently. So anyway, we have this this table of numbers, and these are the composition of the material, the measured composition of the material. So I'm going to click Finish, and then the first thing I do whenever I do a quantification is I always take a look at the residual. And the residual is basically the way that I know whether I've identified all the elements correctly in a material. So looking through this, I see that the residual actually looks pretty good. That when we fit the germanium and the zinc, that we were able to fit them very well. And all that remains, this blue line, is in fact just the essentially the continuum. There are a couple places where it gets a little ugly. One place is under the calcium, and this, it turns out, is because this calcium standard is actually collected on a different day, and the energy calibration is slightly different. And so this S shape is sort of characteristic of a situation where the calibration is slightly off and the peaks don't perfectly align between the standard and the unknown. And then at lower energies, we often see structure down here. And part of that's because there's just edge structure, meaning that there are absorption edges in the continuum. And that's what we're seeing here. Part of it is also because of chemical effects. These transitions are due to transitions where the electron might have started in a valence shell, where chemistry actually does play a role. So that could be why we're seeing this. But generally, this looks pretty good. It looks like we haven't missed any elements in this particular quant process. So having done that, I'll then go and I'll take a look at the report. So there's a series of tabs here. We work most of the time in the spectrum tab. There's a report tab and a command tab. We'll get to the command tab in a minute. But the report tab basically records information about what you do as you're doing it. And it's actually saved in an HTML file that you can then go and open in a browser later. And it's actually stored in a directory, your DTSA-II reports directory under the date. And in that way, you can actually go and review reports from previous or work from previous days. So look at the report. It tells us what we did, fit to an unknown. It tells us what the standards were. It actually has a link to those particular files, so you can reload them. It has a link to the original spectrum, so you can load it. And then it has a table of numbers that is very comprehensive in telling you what you just did. It tells you about the matrix correction in the ZAF row, tells you about the K ratios. Those were the ones that extracted from the spectrum, and they are relative to the standard you used. So the calcium, for example, is relative to the calcium fluoride. And then the MAC is the mass absorption coefficient. And you'll notice that there are error bars associated with all of these numbers. And when you actually get to the mass fraction row, it provides estimates of uncertainty due to the various different contributions. So in this case, we have oxygen measured at about 38%. And it's saying that there's actually a fairly large uncertainty. And that's largely because there's about a 10% uncertainty in the MAC for the oxygen in this case. And this is this estimate of the uncertainty is the estimate given by Chandler, who is the source of most of the mass absorption coefficients used in this software. And when you propagate that uncertainty through all of the matrix correction, you end up with a fairly large uncertainty. So oxygen's hard to measure, and in fact, the error calculation demonstrates that. Other elements, you end up with a lot less uncertainty. So for example, the titanium is 7%, and the uncertainty of that is a few decimal places down from that. So we have this table. Now that's great. It's not very convenient, however, for entering it into reports and the like. So we have mechanisms for entry it into reports. So I'm going to show you one of them. And I'll also show you an example of how you use the command tab. So I'm going to select all the spectra here. And there is in the command tab, this command tab is actually basically a little Python interpreter inside DTSA-II. And it allows you to perform various commands. And so this first command that I do basically just selected, or the selected spectra up there. It's a list of the selected spectra. And so what I'm going to do is I'm going to tabulate the selected spectra, and I end up with a table of numbers that I can then go and copy and go open spreadsheet and just paste them in like that. So that's really convenient for being able to get your data out. So tabulate's actually a fairly sophisticated function. It has lots of options, and the way that you can examine those options is using the help function. So there are a lot of functions within DTSA-II built in for supporting spectrum analysis, and you can help tabulate. And the help function will tell you what they are, or tell you what they do. The dir function will tell you what functions are available. So this gives you a list of all those functions, and you can use, again, the help to come up with information on each of these functions. And so that's just a very, very brief introduction to the command line, but it gives you an idea of some of the things you can do. It also gives you an idea of how to export data. Okay, so that's a very, in brief, how you do standards-based quant. So the next thing we're going to talk about is simulation. We could go to another tool called the Simulation Alien, and it'll allow us to do simulations of various different types. So there's an analytical model, and then there are Monte Carlo models. The analytical model basically uses a phi rho z-like calculation to do a simulation. And in fact, that when you do that, it will be incredibly quick. I'm going to change that to 500 because that's actually what the dose is. And it's done the simulation. And you will notice that the simulated spectrum is actually fairly close in intensity to the measured spectrum. And that's because of the way that we set up the detector. So I'm going to speak a little bit about detectors. Detectors are set up under preferences. And in my particular set of software, I have a lot of detectors because I work with a lot of different people. And so I've set up a lot of different detectors to work with various different people. But basically, detectors are associated with an instrument. So you can create a different set of instruments, and then you can set up the parameters for that detector. At an instrument, you can add a detector here, and then you can set the parameters for that detector. Give it a name, a window, some geometric settings, all of these things. Most of these settings actually don't matter that much for quantification. Where they really matter is simulation. And that's actually the reason they don't matter for quant is because we're using standards. And that's kind of the magic of standards, is that they eliminate the need for us to know things like the window and the dead layer thickness. The other reality is, too, that actually a lot of these parameters don't make that big a difference. So I don't stress too much about them. Usually what I end up doing is actually when I create a new spectrum, I import a lot of these details from the spectrum directly. And that turns out to be often a very good, quick way to do it. But make sure that the elevation angle being critical for standards-based analysis, because the matrix corrections depend so much on that. The thing that's really critical for simulation is this sample to detector distance, because that really determines your solid angle. That combined with the detector area define your solid angle. And that's really how many of the X-rays that were emitted from the sample are going to be collected. So detectors are really important. And if you get this right, you'll see, like we just demonstrated here, that when we do a simulation, you actually get very close to being able to simulate your measured spectra. And that's really, really nice to be able to do, because that really allows you to sort of dry lab experiments, meaning you can figure out what your limits of detection are going to be on the desktop without ever going to the instrument, because you know that you can simulate a spectrum sufficiently well that it'll give you roughly the right limits of detection. Okay, so tools, simulation alien, I'm going to go and do a Monte Carlo. And I'm going to Monte Carlo the same material. I'm going to go for 100 nanoamp seconds in this case. And I can actually, because of the Monte Carlo simulation is really kind of cool, you can turn on and off various X-ray generation modes. If you want to see what a continuum only spectrum is, you can leave these two on and turn off the characteristics. Anyway, lots of fun to be had with that. Next, so Monte Carlo. Monte Carlo is, let's go and look at this. This is going to take a little while to do. So while I'm there, I'm going to switch over to this presentation and just discuss a little bit about Monte Carlo. Monte Carlo tracks the trajectories of individual simulated electrons. So you can see that's what it's doing right here. It says it's done 140 out of 1,000 electrons it's going to track. And for each electron, it scatters a number of times, maybe 500 times as it goes through the sample. At each scatter point, it deflects the electron. And at each scatter point, we evaluate the likelihood that during that last little bit of trajectory that it produced a core shell ionization. And then we also evaluate the likelihood that it produced a Bremsstrahlung X-ray. And then we track these X-rays that could be generated back to the detector. And we take into account things like the absorption by the sample, the detector efficiency. We scale for the simulated dose, and then we convolve with the detector function. So when we look at the report for a simulation, we find that it tells us what we simulated, along with all the various different parameters. You can actually change a lot of things, like you could rotate the sample, you can tilt the sample. And this, while it's not important for a bulk sample like what we're simulating now, is actually useful when we get to the other types of samples that you can look at with a Monte Carlo. So other things you're going to get out of Monte Carlo are emission images. So these are images which show you where the X-rays that you actually measured came from the sample. So this is interesting because, as you can see, for these various different characteristic X-ray lines, they actually come from different places on the sample. So oxygen is a soft X-ray, and so it's strongly absorbed. And so whereas it would be generated fairly deep into the sample, you actually only measure the ones that come from fairly close to the sample, surface of the sample. And you can see that because the oxygen emission image is fairly flat, so pancakey. Whereas the calcium K X-ray is a little bit harder, so it's not as well absorbed. And you can see that it's actually generated deeper in the material. This is important, and this is the mechanism that allows you to do thin film measurements. The germanium is somewhere in between, but you'll actually notice if you look carefully that the germanium emission volume is smaller. And that's because the overvoltage is lower, meaning that it takes a more energetic electron to ionize a germanium than a calcium K line. And so that means that we have actually a smaller volume from which the X-rays are emitted. So other pieces of data that you get out are the fractional emission depths and volumes. And some of this is actually kind of surprising. So let's take the germanium K line here. And I'm going to focus on the volume. And you'll see that the third from the right column, the 50% volume, it turns out that 50% of the X-rays are actually generated within a very tiny volume where the beam enters the sample. And so that's about 1/4 of a micron squared. But if you wanted to go all the way up to 99%, the volume necessary to generate 99% of the signal, you'll find that it's actually 4.3 micrometers squared, which is to say that on one hand, the X-ray signal is coming from this 4-micron volume, but the other hand, most of the, or at least half of the X-ray signal is actually coming from a very, very tiny volume, which is why people have observed that when you do X-ray maps, you actually get higher resolving power on elements than you would expect from the simple excitation volume argument. So the Monte Carlo is going to generate a couple of spectra. There's a called noisy and emitted. The noisy one is essentially the spectrum that looks like what you're going to measure. The emitted one is that same spectrum, but before it was convolved by the detector. So this is like if you imagine you had a perfect detector, 100% efficiency and 100% resolving power, you would get something that looked more like the emitted spectrum. They're both informative in their way. The noisy one is more like what you're going to measure. So finally, one of the real advantages of Monte Carlos is the fact that Monte Carlos are so good for modeling complex geometries. So one of the things that's often difficult to know is if I have a particle, what will the effect of its particle nature have on our measurements of composition? So that's sort of a question you could actually investigate using a Monte Carlo, as we've kind of demonstrated here. And in fact, there are a lot of different models you can use. So spheres, cubes, inclusions, pyramids, cylinders, hemispherical caps, equilateral prisms, buried layers of materials. All of these are available through the user interface. And if you're willing to dig into the scripting, you can actually do a whole slew of different models too. So that's the Monte Carlo. And if we go back, we've finished that simulation. I should say this simulation actually took longer than many do because the simulation, basically the duration is proportional to the number of characteristic X-ray lines. And so this material has a lot of characteristic X-ray lines, so it takes a while. Okay, but having said that, we now have a spectrum that we can compare to the other two. So we have, we'll get rid of the emitted one, and we'll see. And since I did this at a different dose, I'm actually going to spectrum compare. I'm going to scale them to the same dose. And you can see that actually the Monte Carlo, the simulated, analytically simulated spectra actually look very, very similar for the bulk. And that's a good thing. Says that both the models are actually working reasonably well. Okay. So one of the nice things about Monte Carlo simulation is you can actually quantify the simulated spectra. And so how would I do that? I'm going to actually skip the details of that, but I could actually simulate all the standards and go through the whole process. And this is often useful if you want to investigate odd geometries or how an inclusion will affect, or even the effect of, let's say, secondary fluorescence. You have a small inclusion and you wonder how it will differ from whether that same material in bulk. These are all questions you can go and answer by the Monte Carlo simulation. So I'm going to go ahead and get rid of these all and move on to the next part of the talk. And that is the spectrum bundler. The spectrum bundler is a tool that is designed to help you to create the best possible standards. And so I'm going to load in, okay, again, these were collected on a different instrument, so I have to go switch over to that instrument. And before I load them, and we're good. Okay, so I've collected these calcium fluoride spectra I want to use as standard. This is my standard mode of operation. I usually collect multiple spectra for each material. And then what I do is I combine them together to create I sum them together to create one standard for this particular material. Why do I do that? Well, I'm going to basically use a tool called the spectrum bundle, a standard bundler now. And I'm going to take a look at these spectra. So I selected the 5 over here. They're listed here, along with the probe current and lifetime, which you can update here. You could also specify the composition of the material, which is actually already in that spectrum, so I don't need to do it. But now I go to this next page, and it tells me that actually, even though I can't see it by eye, that one of these spectra is actually different from the rest. So this score here is basically evaluates each of the spectra against the mean of the other spectra. So a score of 1 means that the spectra only differ by count statistics. So that's what you want. A score larger than 1 means that they differ by more than count statistics. So this particular spectrum with a score of 3.8 is the worst of these. It differs by substantially more than count statistics. And so I'm just going to remove it. And when I do that, I find that the rest of the scores actually come back closer to 1, which is to say that that one spectrum was an outlier. That's why I collected 5 spectra, because I now can evaluate the spectra against each other and be more confident that I have a high quality standard. So more information that I could enter in. And now I'm going to finish. And what it's going to do is it's going to allow me to save these standards in somewhere. And I'm just going to put them in here for the moment because I don't actually need it. It creates a sum spectrum, which represents the sum of these 4 spectra, since I actually only summed the 4 that were similar to each other. OK, so there's that. Now, why would we want to do that? Well, standard bundler allows us to get these high quality standards that we can then work with. Another reason you might want to work with standard bundler is because of references. Now, references are sometimes necessary. And so I'm going to give you an example of when a reference would be necessary. And that's for if I wanted to use this NIST glass called K412 as a standard. So the problem with K412 is that it has a lot of peaks that are very close to each other. In particular, these ones in the sort of the 1 kV to 2 kV range and in the below 1 kV range. They're not overlapping per se, but they're sufficiently close to each other that it doesn't go down to background. And so we're going to need actual references for these, so peak shape references, so we can use these to quantify. And so the spectrum bundler actually helps you to do this. So I look at the scores look relatively good. And when I get to the references page, it actually asks me for references. So I'm going to select another spectrum to use for my oxygen reference. I'm going to select a spectrum to use for the magnesium reference. I'm going to select a spectrum to use for aluminum, Al2O3, silicon, and finally iron. Those are all the peaks that have interferences. And when I select finish now, what it's actually going to do is create a spectrum bundle, which is a file which contains both the original standard spectrum and all the references. And this makes life so much easier because it means that now, if I wanted to go and quantify, I'm just going to demonstrate that these standards actually work. Now, if I want to go quantify this, I can use the standard option and go and get these standard bundles that I created, which have the Z STD. Use those. Now you'll notice I'm sort of cheating here, but this is actually a good check. I'm using the standards I created from these spectra to quantify the spectra, and I should get very good results. So let's just do it. And in fact, I do. It turns out that if you know much about K412, it's actually the certified composition has an analytical total of 99.16%, and the measured sum that we get for these is very close to that. And these values are all really excellent, which is to say, the software works as it's supposed to. It's able to quantify a standard created from a spectrum and get the correct result back. Okay, so having said that, think I'm at the end of my time. I had a little bit more material, but I don't want to go over long, so I'm going to cut it short here and ask if there are any questions.
Ed, you're muted, and I think John Fernell had a question.
Oh, yes.
In the Q&A.
Yeah, thank you, Nicholas. Yeah, there's a detailed question regarding whether or not the matrix correction used in DTSA-II has been tweaked for the mass absorption coefficient database.
Well, Nicholas, Nicholas, can you see the Q&A box? Click on Q&A and you can read the question.
I can't. No, I can't see the Q&A. But
he's basically pointing out. Ed paraphrased it wrong. He's pointing out that Pouchot and Pouchois, who they tuned XPP ostensibly to the Mach 30 mass absorption coefficient, but you're using Chandler's. So he's just wondering if on that.
No, the answer is no, I haven't. I just use XPP directly out of the box and get good results. So I think the uncertainty in the max is really limiting more than anything else.
Okay. Thanks.
In fact, you can select the same max that Pouchot and Pouchois used, but it just doesn't make that big a difference.
Another question we've received: do simulated standards, how well do they work relative to the measured intensities from real materials?
I would not use them typically to do quant. I will. The only time that I would use a simulated standard would be, let's say, if I was unable to get the material I needed. Let's say I wanted to quantify plutonium, for example. I might use a simulated standard, not being able to get anything better. But as with all standardless analysis, and this is just a form of first principle standardless analysis, you'll find that the errors will be fairly large. So it's not recommended.
Okay. We had another question regarding the first calcium peak is not simulated well. Why is that?
Oh, the calcium L line.
Yeah,
would be. Yeah, the calcium L line is incredibly hard to differentiate from carbon. Yes.
Yeah, I think that and Hendrix gave a similar response. Let's see. We also have, are there any ideas to add or tools that exist that allow one to apply it to spatial data so we could have quantitative mapping feature using EDS?
Let me make an advertisement here for my other tool, which is the Neill, the Julia toolkit, which is actually focused largely around spectrum images too, and that'll do a really good job. There's a recent article in Microscopy and Microanalysis which describes using it for that purpose.
Excellent. Well, thank you, Nicholas.
All righty, thanks, Ed. Thanks
to
everyone for organizing this.
Great talk.
Okay, we're going to move on to our next talk. Let's see. Our next speaker is John, and I'm just looking for the PowerPoint here. What's going on? Forgot. So our next speaker is John Donovan. He's a former director of the microanalytical facility at Camcor at the University of Oregon, and he's the president of Probe Software, which distributes Probe for EPMA and Probe image software for electron microprobes, and he specializes and has a long history in developing software for EPMA techniques and quantitative microanalysis.
Thanks, Ed. I'll share my screen, I guess.
Mm-hmm.
Everybody see it? Everybody seeing that?
We can see your desktop.
Great. So I'm going to talk about 3 programs today, 2 right now, CalcZAF and Standard, and these are them here. If you download the CalcZAF.msi, which stands for Microsoft Installer, you get a menu that you can browse to, here, and then you'll have CalcZAF and Standard, and then PictureSnapApp if you install that. But you can also just put a shortcut on the desktop. So I'm going to just start from here. And they hit a little bit of history. CalcZAF was this is back in the day when we were developing some of the new comparing some of the different models for matrix corrections, and working with Paul Carpenter and John Armstrong at Caltech. John started with first documenting most of these corrections, and that's kind of, and so he had something called CIT-ZAF, which was California Institute of Technology ZAF, and then he had a TRI-ZAF, which was to try all the different matrix corrections. And then subsequently, I came up with a CalcZAF of that version of that, and then the Standard program was originally started as a tool just to maintain your standard database, but both programs have been extended quite a bit to do all sorts of useful things that analysts on both the SEM and microprobe might find interesting. Their CalcZAF and Standard are by themselves a tiny slice of the Pro for EPMA software. And I should probably start out by acknowledging all the help on the software from all the different sorts of people, colleagues I've been working with most of my career. And then in fact, also maybe also mention, now that I think of it, you can get help on CalcZAF it pops up the reference manual, which is about 400 pages of documentation. But maybe even more useful nowadays is pulling up the user forum, which I'm sure many of you know about. And this is a forum on the web, which allows people to post questions and attach files and all kinds of stuff. It's open to all, and I highly recommend that you do that. The screen I first pulled up was this CalcZAF and Standard, and there's a tutorial here that you can go through getting started with CalcZAF. That's what it pulled up first. But if you go back to the main page, I'll just point out for the other speakers, you might not know that their softwares are also on here. So for example, there is the Casino, MCXRay, Hendrix Demers is the moderator of that board. The Reimager, Mia Kraft, DTSA is right here, moderator Nicholas Ritchie. So several of the software packages are already on the forum, and you can ask questions there, read what people have asked before. I think it's a very valuable tool. So that's something to consider. Anyway, so back to this software package here. It's very simple in a way, but it has a number of tools. You could think of CalcZAF. Originally, CalcZAF was implemented to try to test all the different physics analytical models. And so, in fact, if you go to the analytical menu, the first menu you have here is this ZAF Z calculations. And you can, so there's one grouping of corrections is ZAF Z. The other is these alpha factors, which are more of a historical thing, but they actually do have some usefulness even today. And then there's a calibration curve model, and we're working on a fundamental parameters model. But if you click on the ZAF Z options, you can see there's basically 10 different corrections here, and you can generally you want to use them as they are. You can also pick and choose between all the different models and come up with something that may or may not work very well. The Armstrong Love is kind of a default in many of my packages, but we also have the full PAP and XPP, and along with some others that are more historical. This gives you a lot of flexibility. You can also choose different mass absorption coefficient tables. So line mu was the one I first tabulated, which was based on work from Henke at Lawrence Berkeley Laboratory. The SITC mu was the original Heinrich tabulation, which has a few problems in it, which I might demonstrate. And then the others, these are the ones that are calculated from algorithms. And then here's the FFAST, the Chandler, which is what Nicholas is using. And you can also use a user-defined MAC table. And the version of that file that's distributed with the software is one that has been created by Philippe Pommel at the Institute for Transuranic Elements, and it's really heavily, I should say, targeted towards people who work with actinide materials. But it does have a large number of MACs that are missing in the normal tables for obvious reasons. Anyway, so you can do that. So it really was intended for testing the different mass absorption coefficients. So for example, and you could think of CalcZAF as allowing you to take intensities or K ratios from measurements and running them through all these algorithms. But you can also model things analytically by just typing in a formula or a weight % string or even a composition from the standard database. So if you click on this standard database button here, you actually can select from the standard database any of these materials here, and you could model it. You can also type in a formula. So you could say MgFeSiO4. It has a formula parser. And when you do that, you get a composition based on that formula. And if you click the calculate button, you get a output here, which is useful for people who really want to understand all the parameters that went into the calculation. So these are the mass absorption coefficients, and then it breaks apart the calculation for the pure elements, and of course for the material itself, and then the results here. And if you really want to get down to the nitty gritty, you can go into the output menu and you can click on debug mode is already on, but you can click on verbose mode just to show you what happened up here. Yeah, let me do that. Verbose mode, and you get a lot more of the intermediate calculations. So all the intermediate calculations are shown there. Usually that's not of interest to anybody but someone who's writing code. In any case, you can also calculate concentrations from intensities. In that case, and so for example, these can all be edited. So you can click on an element here, and then there's the concentration, because we're going from a known concentration to a intensity that is generated. So we're essentially running the matrix correction backwards. You can also do get a concentration from an intensity or a raw K ratio or an elemental K ratio. In the case of the counts and the raw K ratio, you would actually be then entering a intensity here in this field, and it would give you the weight percent when you were done. And you'll also notice that when you're doing the intensity entry, you also have to specify a standard. And you can add and remove standards from the run here. This would be from the standard database. So just to illustrate this, you could go to File, and the output format, the input format, I should say, of the file. There's a number of test examples here that you can play with. I'll just use the default, which is CalcZAF.dat. It's just an ASCII file. I can show you the format of the file. It's very simple. If we just open it up with a text editor, it's roughly similar to the original format that John Armstrong came up with. There's a line here, which is essentially what mode you're in, which is this first selection right here. And then there is a number of elements, and then there's the operating voltage, the electron voltage, and then the takeoff angle. And you can have a optional name, and then you have a bunch of flags for calculations, and then the element data. So if we just go back to here, and we have now opened the first example, which is using an intensity calculation from concentrations, and we can say calculate, and then this will do exactly that. We give it the concentrations here, and it gives us the K value. This is the raw, this is the elemental K ratio. And we can see here, we can look at the absorption correction, the fluorescence correction, the atomic number correction, which includes backscatter, and stopping power calculations. And then we have the total correction here, which is essentially these three multiplied together. This breaks out the stopping power and the backscatter correction. And this is a F of chi, which is essentially looking at the total absorption correction. And then we have some things like the critical excitation energy, the over voltage here, which is a critical excitation energy divided into the operating voltage, and then also the average mass absorption coefficient in that compound for this element. We can now click this next, load next data set, and when we click that, you'll notice that it's changed the modes to calculate weight concentrations to intensities, because the next data example has a 1 there. So that's now using this next option here, which is to calculate concentrations from intensities. And you'll notice, because this is a raw count, this is net count, so these all have to be background corrected for both the standard intensity and the unknown intensity. And then we have the standard we're using. The standard here you can see is magnetite for iron. For silicon, it is SiO2, and for oxygen, we're using the magnetite again. And these are the standard intensities here and the unknown intensity. And these can be in raw counts or counts per second per nanoamp, whatever you want to use, but they need to be similar units to each other for both the standard and the unknown. I think it goes without saying that everyone knows the K ratio is the unknown intensity divided by the standard intensity. And that's essentially what we're going to do here. We're going to divide this unknown intensity divided by the standard intensity. And when we click calculate, we get the calculation here. And so you can see again the pure element factors here. And then again, the details of the matrix correction here. For this particular matrix correction, if I then go to the analytical menu, ZAF, FIRO-Z, I can select a different one. I can click on PAP, for example, and then I can calculate again, and I get a different result using the PAP method. And in fact, you can go through all of these options by performing calculations for all the matrix corrections by, I'm sorry, here, let me show you here. So you can use all matrix corrections right here. So if you use all matrix corrections, it's going to run this calculation for all the 10 matrix corrections. And so I'll click calculate now, and you'll see that it's going to run through all of them. And it should give you a little summary and output those to ASCII files that are tab limited, so you could import those. And you can also have the option to export that to Excel. And then there is Excel. It's just putting each one into a separate page right there. So here you have the different output options here. and all the sum of all of them right here, or I should say the tabulation of all of them right here. And you can say you want to save that, give it a file name, and then you can, and then it gives you an output in your log window here. This window is called the log window. It just kind of, all the output goes through this window, and you can cut and paste from it, whatever you want to do. You can have it saved as a file and things like that. If we go to the next data set, so that was calculating iron silicate from intensities, sorry. We can click the next data set. I'll turn off this use all matrix corrections. So here's the next material. This is a NIST alloy, steel alloy. And again, we can calculate all the matrix corrections. And we can also do things like plot up the phi-rho-z curves. This might be a little bit messy, but so we can actually look at the generated versus the emitted intensities as a function of phi-rho-z. We can either look at it as a function of mass depth, or we can plot the micron depth here. It's assuming a density, which is 5 in this case, because that's the density that was in the input file, which obviously is a nominal density. But you can kind of see, for example, that things like nickel, the generated intensity and the emitted intensity in green here are very similar. Whereas something like molybdenum L, which is a much lower energy X-ray, you can see the generated versus the emitted intensities are quite different. And that just reflects the absorption correction. All right, and we can look at the next data set. And that is a calculation of hematite from raw K ratios. And so there's a number of examples here, and you can go through these if you want. You don't have to plot the phi-rho-z curves. There's just a number, and this is one where we're calculating excess oxygen in the magnetite. Something that some of you may not be aware of is that having that missing oxygen is actually a very important thing in the matrix correction. If you actually are analyzing something like magnetite or hematite and not including the excess oxygen, all your elements will be off by some fraction. The most effect is on the major elements, on the iron. And so it really should be included. It's very similar to the situation where you're calculating, say, water by difference in a hydrous glass. If you don't include water by difference in the matrix correction, all your elements will be off a little bit. And it's enough to throw off the water by difference calculation by 1% absolute in the case of a, say, 5% water in an alkali glass. So it's a surprising effect, something that, especially the iron surprised me because I wasn't expecting an iron K alpha to be so affected by absorption by oxygen, but it just goes to show you that physics is very unintuitive. All right, so we can go on to the next data set. Again, this is doing silicon by difference. So you can choose, you can have all these elements done by different parameters that are set up in the calculation options here. You can say an element by difference, but you can say whether you want stoichiometric oxygen calculated with it. You can put the density in here. You can display results as formulas. You can do stoichiometry to oxygen. So you can have an element that is, so for instance, calculated relative to the oxygen. That can sometimes be useful for carbonates. You can do stoichiometry to another element. This is something I work with Ed Vicenzi on at NIST, which was doing hydrogen stoichiometry to excess oxygen. And that's a lot, but it basically, there are certain compounds where you actually do need that calculation. Tourmalines and other types of hydrated minerals. And then this is kind of a relatively new calculation that we added in here. And this allows us to calculate the excess oxygen from the ferric-ferrous ratio. It's basically based on the method of Droop. I said et al. There, it's actually Droop only, 1987. And it allows the program to implement some code, which I worked with Andrew Lowcock and Aurelian Moy on, which looks at the charge balance of all the cations and anions. And so if you give it a cation ratio and an oxygen ratio, did I already move on to, yeah, I already moved on to phthalate, unfortunately, because that's all going to be FeO. Let's see, but do I have another one that's magnetite? Doesn't look like it. Okay, let me go ahead and reload that database file. What are we doing on time? Looks like I'm gonna run out of time here pretty quick, but anyways, let me just say that you can do charge balance calculations for excess oxygen, and it works surprisingly well. And again, this is just a very tiny slice of the Pro-free-PMA package, which has a lot more options in it for that kind of thing. There's also a few things that are interesting, I think I'll just want to get to before I switch to the standard database program. You can do things, this is John Furnell worked with me on this. This is basically where you can put in your background intensities, your beam current, your standard intensity, and the concentration of the element. And so you can just put in some numbers here, whatever you want. And if you have these numbers, you can then say I have 1% of the element there, and then you can say calculate the detection limit for a given integration time. So let's put in 10 seconds, and it gives us a very good detection limit because my background intensity was rather small. Let's see if and that's a 1% is a high concentration. If I put in 0.1%, you can see the detection limit is a little different. There you go. And then this is the concentration. You can put it in the concentration instead to try to get the same number back out. And if I count my zeros right, should get about the same number. And it's close, 10 seconds. Okay, so there's that. There's also this kind of a useful little, this is not Monte Carlo. This is just using simple analytical expressions. We'll do the Monte Carlo in a minute. But you can put a composition here of some material and a density, and you can put in a voltage, and you can calculate the 99% electron range based on this very KO formula. I'm not going to try to pronounce it from memory. And then you can also calculate ranges for individual elements within that compound. So you can look at the range of oxygen, which is, as Nicholas pointed out, low energy elements are going to be produced all the way down to where the electrons come to rest. But if you look at something like iron, you're going to see a very different situation where the ability to create an iron shell ionization will end at about halfway through this electron interaction radius, because the overvoltage has dropped below the excitation energy for iron. And you can also look at transmission of that X-ray in that material. You can give it an arbitrary energy X-ray in that material, and you can also look at energy loss. So these are all kind of interesting things to explore interaction volumes and what you might, in a very quick and dirty way. It's not anywhere near as accurate as the Monte Carlo simulations, but it takes a lot less time. And I think, oh yeah, and then there's a temperature calculator here where you can put in a material and calculate temperature rise for a given beam current. You'll notice here aluminum at 30 nanoamps, you less than 1 degree C, put in something like epoxy, which has a much lower thermal conductivity, and you see the temperature rise is 1,000 degrees C. And that is why we vaporize epoxy when we hit it with the beam. All right, and then there's lots of tables here where you can look at the, not just for the K, L, and M lines, but also for all the other odd lines. You can look at emission tables, fluorescent yield, whatever you want. And these are all tabulated. And there's lots of options for creating new versions of tables. And then there's the standard database, which I'll go to now because we're going to run out of time. All right. So if we go to standard database program, again, this program started out merely as a way to maintain the standard database. And you could think of it, so whereas CalcZAF is more targeted toward the analysis of unknowns, you could say, for testing the matrix corrections. Of course, you can run the matrix correction forward or backwards, as I mentioned. Standard is really more looking at knowns. So you basically have a number of databases you can open. The default database is standard.mdb, where MDB stands for Microsoft Database. And there's the American Mineralogist Crystal Structure Database. There's Dana Minerals DHC. There's the ore minerals from Dana, SRMs from NIST. So there's lots of different databases here you can reference for doing various kinds of calculations. We'll just open the standard.mdb file. And so this is kind of basically the standards that I distribute for everybody to use, but you can use your own database much as you want. You can import, export standards, and you can also create standards from the Kamika standard database or from the Joel database. And so if we kind of look at one of these standards, we can just double click it and you'll get a quick calculation or display of the concentrations, K factors, assuming a nominal takeoff angle and all those kind of things, which of course you can change. You can change the conditions whenever you want. That's just what is currently being used. And then you can get an idea of the matrix corrections here. This is the K factor, the elemental K factor, and then the ZAF correction, atomic percents, and a little formula there if that's interesting to you. You can modify these compositions easily by going into the this standard menu for modify, and here you can display it in different modes. You can also reference this in terms of what material it is, and you can actually add in a EDS spectra or a CL spectra to tag with that standard database. You can also add a whole bunch of extra text here. Many users have asked me to allow them to put in all kinds of other information about that standard there. So there's that. And then you can also, of course, list them by average Z, list just the ones that are selected. Let's see. You can also do things like you can search for a standard name. I can say SRTIO3, and it's going to find the SRTIO3 standard for me. You can find all standards within a specific range of a particular element. You can do a match. You can find a composition that you can say match this composition. You can enter in this composition in weight percent, and then you can say match that, and it will go through all the standards and try to find a match for that particular composition. This is not going to be very interesting because I just typed in SRTIO3, I realize. But, and so it's going to say that strontium titanate is the closest match, of course, and then celestite strontium sulfate is the next best match, but not a great match. You can also change the match database to one of the other databases, like for instance, the DHC database or Dana's or the ore mineral database. So it's a nice way of taking, if you have an unknown mineral and you say, what the hell is that? You can try to match it to one of the known minerals, which is kind of cool. And then you can also, there's a modal analysis option here. I won't go into that because of time, but you can also calculate nominal interferences. Let's see, let's put in something that might be a little bit more interesting. Like maybe a, let's see. Okay, let's see, how about, okay, let's put in that Hastelloy again. So if I calculate the interferences with that, because there's a lot of elements in it at trace levels, it gives you kind of a little output here of each X-ray line and what could possibly interfere with it. So this at least gives you kind of a nominal idea of what you might look out for in terms of interferences. Of course, if you want to do the interference correction, you'll have to do that in ProFreq. And then there's some stuff here which I think is pretty useful. There's two types of Monte Carlo simulations in this program. Well, there's the MQ, which is the historical. It's the original Monte Carlo code written by I think Robert Michaelbust and others at NIST back in the day when it was called NBS, National Bureau of Standards. So there's two options here. There's Penetma, the full. So this is all based on Penelope. Penetma is a version of Penelope, the electron photon transport Monte Carlo program. A very large code, and this gives you a graphical user interface to allow you to utilize it in a very efficient manner. And so even someone who knows very little about the details of Penetma, for instance, myself, can actually do all kinds of spectrum simulation with that. And so we can put in a compound here, and I'm not going to do this for very much, but you can put in a beam energy and a takeoff angle, and you can tell it how long to calculate. The dump time is how often it updates the graphics here. And so if I say create an input file and I say run it, it's going to start the calculation. It starts the Penetma software up in a command window. It's a Fortran program, and that's sometimes a little bit tedious to work with. So having the ability to have a user interface is pretty interesting. I noticed that I set the minimum electron photon energy to 1 kilovolt, so it's not going to be as interesting a output as I might have hoped. This is looking at essentially the natural emission of the material. So the X-ray lines are they're at the natural width, so they're going to look very skinny. And of course, if you are going to try to simulate this for a detector, as we do in ProFreq, we actually convolve this for a given detector type and resolution. So we can simulate EDS spectra and WDS spectra, but it's been convolved. This may not. Oh yeah. So here we get a kind of a quick spectrum here, and we can look at the. We can plot this up on a log scale. As you can see, this is all continuum here, and I'm cutting it off at 1 kilovolt because the lower energy X-rays take much longer to calculate. Penetma actually does a really interesting thing. It actually tracks every photon, not just to the detector, but to other atoms. And so if there's a secondary fluorescence effect, this program does a really great job of that. And you can look at the backscatter spectrum as well. So I'm going to just cancel that for now. The cancel button is always here in the main window, and close this. And then I'm going to pull up something which I think is maybe probably the most interesting thing I'll show today, because this is something that is a big problem in microanalysis. And this is where people are analyzing close to the boundary of a grain. And you might not have any electrons incident with the boundary grain, the grain on the boundary. But because of secondary fluorescence, because the X-rays are produced isotropically, at least the characteristic X-rays, they're emitted in all directions, including towards that boundary. And if there happens to be an atom in that boundary material, which is easily fluoresced by that X-ray, then you're going to get the emission of that characteristic X-ray, and your detector, whether it's an WDS detector or an EDS detector, it will detect that. And so you will think you have a trace amount of an element in your measurement when you in fact don't. And I was at a AGU conference a few years ago, and I was watching some presentations, and every single one of them was showing diffusion profiles that were actually fluorescence artifacts. And it was a little bit disappointing, to say the least. Since then, we've published a paper in chemical geology, so I hope that more and more people are aware of this problem. But if you want to know if it's a problem, you can do some so this is where you can put in a beam incident material here, a boundary material here, and then you want to have a primary standard. And so you can calculate these. These calculations are set for default to run about 10 hours each. So 3 materials would take 30 hours. But once you're done with that material calculation, you can calculate these boundary effects for any takeoff angle at any beam energy. So it's extremely flexible, and it only simulates a vertical mirror boundary. So it's one shortcoming. You have to use the Panetma or Nicholas's software if you want to do a more unusual geometry. But if I put in copper as my beam incident material and cobalt as my boundary material, and using the cobalt standard because I'm going to measure the cobalt X-ray. And by the way, this was a problem pointed out by Castang 60 years ago. So this is something that's been known for a long time, and we really have not dealt with this properly, but at least knowing about the problem is half the battle. And so if I run to extract these intensities from this nominal calculation, it only takes a few seconds because I've done the 30-hour calculation already. There's a whole bunch of materials that you can that are provided with the program that are already pre-calculated. So you can jump right into modeling some different things. And so here you can see that this is not a small problem. This is basically, if you're 1 micron from the boundary, you're going to get 4.5 weight% of cobalt in pure copper adjacent to cobalt. And again, this is not electrons bleeding over into the boundary. This simulates only the secondary fluorescence. Here's 2 microns, 3.5%, 3 microns, 3%. So, and if you want, you can plot this up as a log scale. So you can see this goes out 40, 50 microns from the boundary. This is the boundary being this line right here. The copper on this side and cobalt on that side. I had an example. I'm running out of time here. I'm going to wrap up, but I had a problem approached me from Oak Ridge National Lab, and they say they were getting weird results looking at magnesium, aluminum, and zinc alloys. And they were, and I modeled it for them and showed them that they would be able to detect their zinc component grain half a millimeter away from their aluminum magnesium boundary. In that case, of course, zinc K alpha being a very penetrating X-ray, and magnesium aluminum not absorbing it very well. So these are just some of the things you can do in this program. I think you'll find it useful. There's lots of options here that I have not discussed, but the forum is a good place to learn about some of these. And post your questions and on the forum or now, and I'll try to answer them. I'll leave a few minutes for some questions. Ed?
Thank you, John. I have a question relating to the boundary fluorescence. For people in general, you have this nice tool where you can enter the material on one side of the boundary and on the other. But do you have a general rule of thumb is when you should be really, when the effect is really important in terms of the periodic table?
The effect is important. Yes, and I think you know the answer to this, but I'll tell you. The effect is most predominant when you're measuring a trace element in a material that is adjacent to a phase that has that element in a high concentration. So if you're trying to measure calcium in olivines adjacent to a northite, you're going to have a big problem. And in fact, I can just pull that up really quick here. So I can browse to a compound here. I can say that I'm going to look at olivine. I mean, I have, here's Fe2SiO4. So I load that as my incident material. I load in a northite. Whoops. I think it's right here. Well, here's a northite. And then I put in, say, a calcium standard. It doesn't matter what I use. Those are compounds there. Also, the pure elements are down here. Doesn't matter what you use as a standard. It'll figure it out. So I can put in calcium here. And like I say, I'm going to measure calcium. And so I can go ahead and calculate now. So this olivine has no calcium. Now, if you're unknown material, in beam incident material did have some calcium, then it would handle that. And so you'd see this not tailing off to zero, you'd see it keep going out. And in fact, you can see that even at 50 microns away, we're getting about 100 ppm of calcium. And we're getting a 1,000 ppm at somewhere within 10 microns. So I've seen so many of these curves that people think they can derive thermodynamic principles from, and I have to tell you, you're barking up the wrong tree. So use this app to give you an idea of where you may be in trouble or not with your trace element analyses near boundaries, because this isn't necessarily 50 microns might not be considered close to a boundary, but if the microprobe can do 100 ppm quite easily, actually, with just a little bit of effort. We've demonstrated 2 to 3 ppm t-test 99% confidence for titanium and quartz. So that's another big problem, is people measuring titanium and quartz, and there's a rutile grain next to it. So that's not going to work. Thank you, Ed.
Makes me wonder if this type of effect is even considered in complex materials where you're doing micro-XRF, where you might get equivalent.
Yeah, I mean, micro-XRF is a very sensitive technique.
Yeah.
Yeah.
Okay. Let's see. So I don't see any other questions in the Q&A. I think we have time now for a break or / discussion. So if there is something that either Nicholas or you didn't have time to go over, maybe briefly, is that the case?
Sure, or yeah, whatever people want to do. I'm good to hang out for some questions or more demonstrations, Nicholas.
We do have a question from Nestor Zalusic. Is the secondary fluorescence calculation only due to characteristic, or do you also calculate Bremsstrahlung fluorescence?
Okay, so both are calculated. So in the example of the zinc calculation, so it calculates both. And in fact, maybe the best way to do it is to, am I still sharing my screen?
No.
Okay, let me share my screen again. Let's see. Okay, so if I go to where those calculations were performed, and that would be so when you install these apps of mine, they create a user data folder, and in there it's going to put some things like, here's the CalcZAF, that example data, that you saw, and then also it'll install this Panetma 12 folder here, and this contains, so here's that Final program that did those extractions for those secondary fluorescence calculations. Here's the Panetma PD base, is all the physics parameters there. Panetma, and then PenFluor is the one that does the 10-hour calculation, so you can do the secondary fluorescence calculations. So if you go into the PenFluor program here, you can let's see, maybe sort this by date. See, I'm trying to remember. Hang on a second. So, okay, so if you go back, so what you're going to have to do is go to the Final folder. Sorry, I had to remind myself where this was. So it's in the Final folder, and then it's gonna create the here are all the files that it created for this calculation, and the file that you really want to look at is the one that's called kratios.dat. And if you open that up with Excel, I think this will just open with Excel. Yeah. Then it's going to give you here are the this is the beam energy, which obviously is going to be the same for every calculation. Then it's going to do the, whoops, I'm not selecting the whole column, am I? Yeah, so here And then here's the total K ratio here. Oh, I think I messed up the file. I did something wrong. Let me try it again. So there's these are, oh, that's interesting. They're not separated by, oh, I think I know. This is the finale output. Okay, sorry. You want to look for with the file you want to look for is actually called, maybe it's, no, for some reason I'm not seeing it. I can give you an example. So if you go to like, so here's some boundary calculations here. I will, and let's see, here's some, let me find some folders. Couple, here's couples under couple, that's where it is. Okay, sorry. So here's an example of a material. Let's look at the, you want to run these in batch mode is I guess what I'm saying. And when you do that, you get a K ratios 2.dat and a K ratios 2 Excel file. So let's open that. That's the file I was looking for. So here, this is a little bit more better here now. So here's the total intensity, obviously, and then this is going to give you just the fluorescence only. You have the fluorescence from the phase, the beam incident phase is A, the boundary phase is B, and these are primary intensity. And you can get all these different intensities out, including the matrix correction factors, and it goes out a long way. So you can, so all the data here, it calculates both continuum and characteristic. Here's the primary, and then here's the, this is primary only. This is the concentration. Sorry, I haven't looked at this in a, here, total intensity. And then, anyway, all the things you want to know are here. And I think it's all documented on the forum. If you want to take a look.
All right, excellent. Thank you, John. Nicholas is going to join us again because there's an optimization tool he wanted to relay to everyone, and where to get help videos and all that.
Sounds good.
Okay, let's back again, get things started up again. So you should just be seeing DTSA-II starting again. So if I had a couple extra minutes, which I do now, I was going to show you one more tool. And that tool is the optimization tool. So this is actually very similar to something John had showed you for WDS. This was the tool that John Furnell and he worked on for WDS, but this is an equivalent for EDS. Basically, it's helps you to try and plan making a measurement. And so how long you should acquire for to get a certain level of precision. And so I have this tool called the optimization alien, and basically it allows you to specify information about your material and then to generate a report that allows you to get some, make some suggestions on how to measure it. So it depends, of course, on the detector you're using. So if this is the instrument I'm making my measurement on, I want to optimize relative to the efficiency of that. And first thing it's going to want to know is, well, okay, so you want to make a measurement. So what sort of standards are you going to use? And so for silicon and oxygen, I might use the material SiO2. And one of the questions it has is basically, so how precise do I want my measurement to be? I could do it to 1%. I could do it to 1/10%. The rule of thumb is that every order of magnitude increase in precision is going to take you 100 times longer. Square the increase in precision, and that's the amount of time it's going to take. Turns out that actually measuring things to 1% doesn't take very long. So I'm just going to go ahead and do that. I'm going to add a series of elements, most of them as just pure elements. And I'm actually going to do this for the material that we measured earlier, or worked with earlier, the ADM material. Calcium, I'll use calcium fluoride like we did before. Titanium, use titanium. Zinc, use zinc. And germanium, use germanium. Okay, let's make sure I've got all the right elements in here. I think I do. Okay, so that's how we specify the standards we're going to use and the precision we desire. Actually, let's change one thing. Let's change this aluminum and make it require not 1% precision, but 0.1%. And so we'll work with that. We'll say, okay, no other elements of interest. We're not going to strip any peaks. So we're going to use all the standards as references because they are suitable as such. Otherwise, we could also specify a reference, which is also would mean that the optimization tool would also tell you how long to collect your reference for too. And then we're going to specify a composition of a material. And we've selected here, this is approximately the composition of the ADM glass that we looked at earlier. And so I entered this earlier. It's a little bit tedious to do it. We would go and do it through the material editor, which looks like this, just by adding elements down here and the amount here. But we won't do that. It's already entered in here. And then it's going to tell us, basically, this is the information that we want. What dose, so how many nanoamp seconds. So if this were a 1 nanoamp beam, we'd have to measure it for 10 seconds. The aluminum would actually have to measure for 13 seconds. That's actually not that long. None of these numbers are that big. That's because to measure to 1%, actually this hits up against my baseline, which is to say that you collect for a minimum of 10 seconds. But actually to get 0.1% with aluminum, aluminum produces a prodigious number of X-rays. And so to get to very high precision very, very quickly, you only need 13 nanoamp seconds. That's slightly different, though, for the dose for the unknown, because, of course, in the unknown, the quantity of aluminum is much lower. And so we need to collect for a lot longer in that, and this is often the case. When you have a pure element, you don't really need to collect for that long because it produces a lot of X-rays. However, when you're collecting the unknown, you typically have to spend a lot more time on it. So ultimately, it generates a report that looks something like this, which you can then go and print and take with you to the lab to plan your measurement. It looks something like this here. It tells you what the materials you need to measure are, and it tells you if you had any references, you needed that, and it tells you basically this is your measurement plan. It tells you what you need to measure and for how long. This is kind of a useful tool. I think it's underutilized, but it can be pretty useful. Because, of course, we can simulate these spectra too, I can actually simulate the whole measurement campaign. And just there we go. We did it. These are all analytical simulations in this case. And then I could go through the whole quant process on these simulated spectra to see if what the tool recommends actually makes some sense.
Very nice.
So there's that. Yeah. So yep.
Thanks, Nicholas. Actually, I just wanted to jump in really quickly. I just figured out. Could you stop sharing?
John, it'll have to be real fast here.
It's going to be really fast.
Okay.
Yep.
Oh, excellent.
Stop sharing. There we go. All yours.
Yeah, thanks. I just wanted to point out that I figured out why I wasn't getting the data output. It's because you have to check this send to Excel checkbox here. So if anyone wants to have the data output to Excel, just click send to Excel. I'll make that bold in the next version. All right, that's all I wanted to say.
Thank you, John.
And thank you, Nicholas.
And Nicholas. Right, okay. We're gonna move on to our next speaker, and that is Aurelian Moy. He's a EPMA specialist Specifically with regard to atomic parameters determination, his research focuses on the development of new methods for quantification at low accelerating voltages by using soft X-rays, as well as improving matrix correction algorithms. And he's going to talk to us about BadgerFilm, something we're really happy to see on the scene. It's a versatile platform to characterize multi-layer specimens as well as bulk, and he's going to tell us all about that.
Thank you, Ed, for the nice introduction. So let me share my screen. All right, so let me talk a little bit about BadgerFilm, which is a thin film analysis program for electron probe microanalysis. So this program was developed at the University of Wisconsin-Madison, the Geoscience Department, in collaboration with John Neill and with the financial support of the National Science Foundation. So electron probe microanalysis is usually used to quantify the composition of bulk samples, but we can also use the technique to determine the composition and the thickness of layers on top of a substrate. So the method to do that is to measure K ratios for the elements on the unknown layers or on the substrate. And these K ratios, which are the ratio of the X-ray intensity measured on the unknown and on a standard. So these K ratios needs to be measured at least at a single voltage, of course, but it's better to measure them at several accelerating voltages. This is the multi-voltage method. And the experimental K ratios will be fitted with a theoretical model that will calculate theoretical K ratios. And to calculate those theoretical K ratios, we need to select an ionization depth distribution model, the famous Vicenzi model, and also a mass absorption coefficient model. So to streamline this process, we have developed BadgerFilm, which is using a very simple graphical user interface. The program can simulate all the elements of the periodic table up to Einsteinium. It implements several Vicenzi models, and it's open source. You can download it at this address. So I'll briefly describe the different options in BadgerFilm, and then we'll move on to a real application. So on the left side, we can choose different options. For example, we can activate or deactivate the secondary fluorescence calculations. We can specify the takeoff angle or the elevation angle of our detector. We can choose different Vicenzi models, different mass absorption coefficient models, as well as some electron ionization cross-section models, but those will not play, they will not have any impact on our calculations today. And then in the middle part and the periodic table, we can define the sample geometry and composition. We can define the number of layers, the density of each layers, and the different elements inside those layers. In the middle table, we will input our experimental K ratios that we have measured on our unknown and on the standards. And on the bottom left, there's the calculate button. And when we click on that, we'll have some results that will be displayed on the bottom boxes. Now also several other options. We can save the data we have inputted in BadgerFilm, and we can load previous data from a previous run. We can also import data from StrataGen or data generated from Probe5PMA. And we can export our calculations, and we can also export the absolute intensities that were calculated by BadgerFilm. So now let's try it on an example. So we'll have a layer of aluminum of unknown thickness deposited on a substrate of unknown composition, but containing silicon and oxygen. So the experimental data that we have to measure are the aluminum K-alpha, silicon K-alpha, and oxygen K-alpha K ratios. And to do that, we'll use a pure aluminum standard for aluminum, pure silicon for silicon, and an yttrium iron garnet for oxygen. So you can download BadgerFilm on this repository, on the BadgerFilm repository. On the release, the most recent version is 1.2.19. You download the zip file, and when you unzip it, it's ready to go. You don't have to install it. You can just double-click on badgerfilm.exe, and it will start the program. So on the left part, you can choose the different, if you want to include the secondary fluorescence calculations, you can input your takeoff angle. So for an instrument, it was 40 degrees. It can be 35 degrees, or it depends of the electron microprobe or SEM that you are using. Then you can select the Faraday model you want to use. Some of them are grayed out. This is because they are implemented, but they have not been tested yet or tested enough. The X5 model from Claude Merlet is almost ready, so I think it's going to be released in the next version of BadgerFilm. So today we'll use the PAP model. Then you can select the MAC, the models that you want to use. I know that Hendrix, the MAC30 database, is working very well with the PAP model, but you can also use the FFAS model if you want. And then I will show you here. So those are the experimental data that were measured on our unknown sample. So we had measurements at 5, 10, 15, 20, 25, and 30 kV, so 6 different accelerating voltages. So our sample is made of one layer on top of a substrate. So in BadgerFilm, it's asking the number of layers, and we'll enter 2 because the substrate is considered as a layer with an infinite thickness. And so on the first layer, we have aluminum. And then on the, so aluminum, we know that it's 100% aluminum. It's only made, we'll assume it's not oxidized. So the weight fraction is exactly 1. So if I right click on this cell, it becomes blue. That means that we have fixed this concentration. It will not be changed by the fitting algorithm. I need to specify the layer density. So it's about 2.7. And the thickness, I can guess what will be the thickness, but I can just leave it by default. If I knew what the thickness will be, I can fix it, so it will not be modified by the program. But here, this is an unknown, so I will leave it like that. And then on the substrate, I know that I have silicon and oxygen. I don't know the concentration of each element, so I will leave it with a white background. So it's a free parameter that will be modified by the fitting algorithm. And now I need to input my experimental K ratios. So for each element, I have 6 different K ratios. So for example, if I select oxygen, I can click on add a kV to the selected element. So it's adding a new entry for oxygen. So I just click until I have 6 different lines. And then I can copy my accelerating voltages and paste them in the energy in kV that are needed. Oops. And then I can also input my K ratios, my experimental K ratios. If I had statistical uncertainty on the experimental K ratio, I can input it here, but I don't have any, so I will leave it blank. And by default, BadgerFilm is selecting the K alpha line for this element, but I could have been working with a K beta line, so I can just type it. Or if I had another element, I can also use the L alpha, M alpha or beta. I can also use the X-ray transition directly, the KL3. So BadgerFilm knows that this is the K alpha 1 X-ray line, but I will just leave it to K alpha. Then I need to input my K ratios for the other elements. So I will just add some lines. One, two, three, four, five, six. Okay, and now I will just input the accelerating voltages and the K ratios. And now I need to define the standards that were used to calculate those K ratios, or to measure those K ratios. So for aluminum and silicon, I'm using a pure standard. So by default, this is what BadgerFilm will consider. So I don't need to enter anything for aluminum and silicon. But for oxygen, I was using an yttrium iron garnet. So I need to define this standard first. So to do that, I will just start a new instance of BadgerFilm. A couple seconds. And now here I will input my standard composition. So I know that I have yttrium, iron, and oxygen. I can define the composition in atomic fraction or atomic formula. So I know that is Y3, Fe5, or 12. I can switch between Weyl fraction and atomic fraction. This is very easy. If my sample was coded, I can take that into account, because if it was coded with a 20 nanometers of carbon, this layer will attenuate the X-ray that are emitted and slow down the electrons from the electron beam. So to do that, I just have to enter to say there is 2 layers, which is the carbon coating and the substrate. And I can specify the carbon coating thickness. If it was 20 nanometers or 200 angstrom, I just enter it. But for our case, we will assume that the standard was uncoded. So just a bulk sample of garnet. So once I have this, I just save it. I give it a name like Y3, Fe5, or 12 standard. I save that. I close this instance of BadgerFilm. And now if I click on the standard cell for oxygen, I can choose the standard that we just have created. And we can see that BadgerFilm have populated the standard for all the oxygen entries. So now that I have defined everything, I can just click on calculate, and BadgerFilm will try to calculate the theoretical K ratios that will be matched to the experimental K ratios. So here are the results. So BadgerFilm is finding an aluminum thickness of 127 nanometers. The target was actually known, it was 122 nanometers, so pretty close. And it also found that there is about 0.33 atomic percent fraction silicon and 0.67 atomic percent oxygen. So this is CiO2 actually. Okay, so the substrate was CiO2. And here on the graph, you can change the scale of the X and Y axis. So the K ratios for oxygen was a little bit high. It was about 2.5 at maximum. And if I double click, I can just have a larger view. So there is a pretty good fitting. For oxygen, the theoretical calculations are underestimated. but overall, this is a good fit. And I can export my data. So I just click this button here, and then the data are compiled in the clipboard. So I can just open a new Excel spreadsheet and paste the data. So at first you have the different models that were used. And then we have the results that we just went through, the thickness layer of the first layer, and then the substrate, its composition. And then you have the experimental K ratios that you have entered and all the theoretical K ratios that were calculated by BadgerFilm. So this is a very easy way to export the data. I will now talk about like two options that may be useful. So for example, in geological materials, sometimes you don't want or you can't measure the oxygen directly, so you will use oxygen by stoichiometry. So if I check these options here, we can see that the oxygen was removed from the data. And then if I calculate, it will assume perfect stoichiometry with silicon. So it will assume a perfect SiO2 substrate. And we can also define another element relative to the oxygen that was calculated by stoichiometry. For example, carbon. This is useful if you are analyzing calcite, or you'll have a CO3 type formula. So you can specify that you want 0.333 atoms of carbon for each atom of oxygen. And another option that you may be interested is to be able to calculate mass absorption coefficients. So we know that for some elements, the mass absorption coefficient is not very well known, and the databases, they may not be very accurate for some of them. So if you check this box here, and check that, you can specify the mass absorption coefficient that you would like to measure. So for example, the oxygen K alpha line absorbed by uranium, and you can specify a starting MAC value. You can guess what will be the value, but you can just leave it blank, or it doesn't matter. And then we'll load some data. Those are data that were acquired by Liovit and Palm on a uranium oxide sample. So this is the oxygen K alpha line measured at different accelerating voltages. And their UO2 sample was actually coated with an aluminum layer. They measured the thickness. It was about 19.6 nanometers. So we just entered that. We know that it's pure aluminum. So we fixed the thickness concentration, and we know that the substrate is UO2. So we just input the atomic fraction, and we fix those values so they will not be changed by the fitting algorithm. And then in the experimental K ratio, we can either enter some K ratios, but we can also enter directly the oxygen K alpha X-ray intensity. So we don't have to measure it to normalize it with a standard. And then if we click the calculate button, it will now calculate the MAC for this X-ray line. It takes a little bit of time. This is basically because we have some fluorescence by the Bremsstrahlung and the characteristic fluorescence too. And so it's finding an MAC of 9,700 about. If we look at their publication, they use Stratagem, and they had to correct their data to take into account the aluminum layer because some X-ray were absorbed by this layer and the electron beam was attenuated by the layer. But they found an MAC for uranium, it's a little small, of 9,300. So this is pretty close to what we found with BadgerFilm, without having to correct the data, just by simulating the layer directly, the aluminum layer directly on the sample. So that's about it. Just one last thing, in BadgerFilm, you can input experimental MACs that you have measured, or if you know that some MACs in the database that you are using are not quite correct, you can input them directly in this experimental MAC file. So it's very simple. You input the element, the X-ray line, the absorbing material, and then the MAC that you have measured. I think that's it.
Thank you very much, Aurelian. Very interesting stuff. In general, if people are asking about how many different voltages should I use to collect the data, do you have a general rule of thumb to give them, or
I will say at least 3. Okay, the best, maybe I can show you if I load. If I load this, try to calculate it real quick. I did something wrong. Oh, yes. The best is having K ratios where the curve is curving, actually. If you have K ratios in the flat part, well, it's harder to have a good fit, but where there's a strong curvature, this is where the fitting algorithm will be the most efficient.
So you might start with 3 and then sort of look where the biggest changes are taking place. And
yeah, I always use 3, Ed. 3 works just great. That, I mean, if you were trying to push the envelope on some situation where you had same element in the substrate as in the film, then you might need more. But Aurelian is exactly correct. Where the slope is the highest, negative or positive, that's where you want to put your measurements. And so it's a really good idea to always model your film if you have any idea what the thickness is, and then that will tell you where you want to measure your voltages.
Yeah. In the case of atomic layer deposition, where the people who do that type of synthesis, they're pretty confident they've produced alumina or titania or whatever it is. Can you then fix the composition of the film and sort of just iterate for the thickness of the film?
Absolutely, yes. You can enter, if you know it's AL2 or 3, you just specify this is AL2 or 3, and if you right click, the cell becomes blue. That means that the concentration is fixed, it will not be changed. So now if I calculate, it will only iterate on the thickness of this layer and give you the answer.
Yeah, and of course that's the mass thickness, and then you need to know the density, which can be problematic.
Sure.
Yes, you can actually just, if you want the mass thickness, you can have these results here, so it's independent of the layer density. But usually you need to know what will be the layer density to have the results in nanometers or angstroms.
Of course. Are there peer-reviewed publications describing BadgerFilm if someone's looking to cite the use of your program?
Yes, there are 2 publications that were published last year in Microscopy and Microanalysis. If you Google BadgerFilm, Microscopy and Microanalysis, you'll find them.
Excellent. Well, thanks again, Aurelian.
Thank you.
Okay. So stepping in for software developer Mia Kraft today is Annette Vonderhand, and she's a research associate in the Department of Earth, Ocean, and Atmospheric Sciences at University of British Columbia in Vancouver. And she has over 15 years of experience using the electron microbeam analysis and is currently responsible for their brand new lab that's just recently been set up there.
Yes, thank you. Let me share my screen. And yes, so I'm giving this presentation on behalf of Mia Kraft, who is the actual developer of the ProbeLab reimager. Unfortunately, Mia couldn't do it. And I want to acknowledge also an NSF grant. So the ProbeLab reimager that I will show was developed out of some frustrations with existing software and as part of this project. And so we thought maybe that the wider community might enjoy that as well. Okay, so ProbeLab reimager is a free tool that allows you to annotate, batch export, and images that you acquired on your microprobe or SEM, and it fills a small gap, I think, when it comes to its capabilities compared to what various proprietary softwares are offering. And one of its advantages in particular, at least to me as a lab manager, is that it is platform independent, meaning that it was coded in Node.js, so it's more like a web browser, and it runs on Windows, various Windows versions, and Macs, and also Linux. So specifically when it comes to creating more customizations, we often like to just have the users play with colors and things and stay away from the main instrument computer, and this helps with that. Okay, so what does ProbeLab reimager do? As the name says, it essentially is geared towards images. It starts fairly quick. You can maximize it, and so it just has one main graphic user interface. And so on the, oops, let me just move some windows out of the way. Here on the upper left-hand side, we can select a directory to look at samples. And so I just go in one for Pathfinder and just open something so that we have something to look at. Okay, so what kind of data does ProbeLab reimager handle? We usually have various different softwares that help you acquire electron images on either electron microprobes or scanning electron microscopes. And ProbeLab reimager lets you work with Thermo Pathfinder EDS if the images are acquired in their point and shoot method or as X-ray maps. It can handle JOL electron images if acquired through their PCSEM software. So that would then be applicable for electron microprobes, but also electron microscopes. It can handle Chemica PeakSide files, and it can handle Pro4 EPMA software files that is developed by Donovan, who's here. Okay, to show you what the options are, we have here on the left-hand side an overview of the files, of the images that are in the directory that I just opened. Again, this is from a Pathfinder analysis. It gives me the comment names of the files, and it gives me their size. And it just looks in the directory what is there. I can store and save and export all these files after I've done my custom annotations, and I will show you that in a moment. On the right-hand side, we have the various custom annotations that we can do, and I will show you examples of all of these. And specifically as it's regarding the scale bar, as well as analysis locations, where EDS spectra or WDS analysis, depending on the software, have been acquired. And down here, we can flip between point data annotations or maps if they are were acquired as well. And in the center, then we see the actual image. Below, again, some information just about the sizes. And then we will see the various things that we can display on this. Okay, so when we just loaded up the software, it just has its defaults, which includes not showing the point analysis. And so every time we make a change, we can just refresh the image. After we made these changes and we will flip to a different picture, it will remember these changes. Okay, so we have our electron image, and usually when it comes to these images, one thing that we like to change is the way the scale bar is being displayed, depending on what we want to do with it. So if it's like for a publication later, it might be we want to make sure that the scale bar is visible for whatever way it will be displayed in the manuscript, or if it's a poster, will the image be part of a larger tableau and will be very minimized, or will we blow it up on a poster and will be really large? And each time we might want to change a little bit the way the scale bar is being displayed. So ProbeLab Reimager allows us to move the scale bar around. The default is that it's in the lower center of the image. We can move it to the lower left. And again, I have to hit refresh to have it displayed. I can show it on the lower right. I can also put it in the upper corners, just depending on what I want to do. And so I don't have to mess with Illustrator or Photoshop forever and try to guesstimate what the length of my scale bar is, if I want to just do a simple change like that. Maybe I don't want to see the scale bar on the image itself, but rather want to have it displayed in a darker bar. And so this is what below center left right gives us. So if this would be, it would show it below the actual center. And it usually tries to match the color relative that the adjacent image has. So in this case, it chooses a black background. If I would, let's see if so here again, it remembered what I chose, so I don't have to hit refresh. And in this case, it automatically chose a white background. And so it always depends a little bit on what the image exactly shows. Now, maybe you want to have more control over that. And so this is where all these options come into play. So there is background color, and maybe I want to make sure that all my images show a white background. So I can just do that, keep the font color on auto if I want. It's smart enough to know that then we would want a white, a black color. And then, so if I then move around, I get consistently a white background. Again, with font colors, I also have the option to choose between white and black instead of letting the software decide that. And so I could also do the opposite, white color, black background, say refresh image. And so I can move, I can really customize it to what I want. When it comes to maybe I want to have the annotation above the scale bar. This is something I can do here with scale type. I can switch between above and below. And so then it would switch it. And again, this would apply to all the other options as well. And then we might have situations like this where we feel that the background is a little busy. We want to improve. We want to improve the visibility of the scale bar, but we don't want to completely obliterate it. And so I could do in this case a black background, but I can change the background opacity to a certain percentage, let's say 75. And now I have a fairly black background. I can change it to 15. Now I have just the faintest black background for the scale bar. And so I can really make my image just the way I would like to have it. If I want to scale the size of this label, this is the option here. It is in percentage. So if I have images that were acquired at different resolutions, I get a consistent scale bar size across. I don't have to worry that my 14 point look different on a 1024 compared to a 248 pixel resolution. So I can increase that. And now it's much larger. And most importantly, sometimes we want to have like, say, all the images that we have with a consistent scale bar. So right now it says auto, but maybe I want to have everything exactly with just proof of concept, 72 microns, and I can type that in. If I want to return to the auto settings, I can just click on these labels in each case, and it puts it all back. If I want to make changes, and so it's very easy to navigate the interface. Now I said we can also have point annotations displayed. So here we have individual points where we acquired EDS spectra. So I can just say select all. If I have a lot of points, that's useful. And then they're being displayed here. They're relatively small in this case, so I can increase the point size. Let's make it really, really large, just so that everyone can see what we're doing. And so we have, again, we have like full control over the size of these annotations. We have full control over the color. So currently it offers red, orange, white, and black. So let's say I just want to have white. I can do that. I can have different types of markers. This is like what Thermo likes to have. There's Thermo round. So instead of has a rounded crosshair, you can also just have a circle or a cross. And yeah, so again, we can change all these things. We can change the size of these annotations. We can also just say, instead of all, I only want to have 0.2 displayed. And if I want to do, yeah, and so with that, I can go, again, it remembers the settings. So again, comically large. So usually we probably just want to have something slightly larger. We get all these different annotations exactly as we would like to have them. Now, there are different ways how now we can build up all our images and export them. The easiest way is if I have like a specific style then that I like, everything in 125% point size, always all the points being displayed on it. And then I can just select all my images in the folder with a Control-Shift. It has an easy mode that I can turn on and off. And what easy mode means, I can then say export selected, is it just names the files after the original comment, but I can also add certain things, certain further annotations like plus points or a date or something. And then I can export it as TIFF, JPEG, PNG, or WebP. So let's do that. And it just goes through and shows me down here where we are, and it's incredibly fast. And so then if we go into the folder, I could have also changed the folder if I wanted. We see that we have like all these exported files in the naming convention that I want. And they show exactly, what the annotations that I'm interested in. Okay, let's say I want to switch things in between. Sometimes I want to have a white annotation. I can store that. Then the next time I want to have a orange point color, and maybe I want to have a scale bar again of my 72 microns. And then I can always store that. Maybe I want to have another one that shows only 0.1 in black, and I want the scale bar to the right, and I can store that again. Oops, that's not. And then, so I can build everything like this, and then I can just say export saved, and it shows them because maybe I want to change their names individually. I can then do that individually, and it shows me each time what I have and exports it. Okay, so this is when we have points on it. Let's say we have an EDS map. I open a different folder. Again, I can mix and match different resolutions. And so here is an example where I also have an EDS map. So now it automatically switches over to the maps. And there I have the option to assign different colors. So I select silicon, make it green. Let's say let's make the titanium pink. And I say refresh image. And boom, here we have that. I can change the order of the layers. If that at times, if they overlap, that can be helpful. I can also change my base layer. So I can have the electron image underneath, or I can just have a black background, a solid color, any solid color, or white. And so again, it gives a lot of options, and the same for scale bars and whatnot. We can make the changes there, and I can add it to the stored ones and have it exported. So very versatile when it comes to maps. And so just to show you, if you have JOL images, of course, you don't have positions. It's similar. Oops. Oh, interesting. Okay. Well, of course, nothing ever immediately works when I just open it. Okay, with the JOL images, it just cuts off the data bar that we have at the end. but same thing, I can change my scale bar to wherever I want and customize that and export it. And then to show you quickly, probe for EPMA. It loads up all the images from your probe for EPMA. Again, it allows me to display the individual points that were acquired on the image. And so I can go through and just have an easy way to batch export in the file format of my choice, what we need here. Okay.
Very good.
That would be it.
Yeah. Thank you, Annette. I can see that Reimager is going to be very useful, particularly if you were generating like an image atlas among other routine images, you know.
Yeah. Or you just very quickly just want to like create documentation or even see what's in the files.
Yeah. Are there filters for averaging or smoothing the X-ray images? Did I see that?
So that is available through the X-ray maps. That was the other one. So in Pathfinder itself, there are all the different kind of imaging filters. And so if you apply these in what the ProbeLab Reimager does is it reads out the TIFF files that Pathfinder creates of the X-ray maps. So you apply everything, use all the advanced filter options that Pathfinder has, save it as map, and then you have the option still to export and change the coloring and all that in Reimager.
The spatial binning. Yeah, very good.
Yeah.
Okay. Well, thanks again. Okay. Well, let's see. We have
One question.
a question. Yeah.
Yep.
Reimager.
Just
what
quick.
specific
So,
formats. Yeah.
Yep. So just to show you again here. So what you can do is what we have available is TIFF, JPEG, PNG, and WebP. And then probably very interesting for the people who use Probe for EPMA is you can also create ACQ files.
Okay.
So for the people who use PictureSnapApp, I think we will hear about it, and all these other ones. The ACQ is the little text file that essentially tells the software the stage to image pixel coordination. And so ProbeLab Reimager can quickly produce that.
It's possible the question was about input formats.
Oh, thank you. Yes. So it reads in the MDB for the positions and the BIM, the image database for the images. So it takes the raw probe for EPMA.
Okay.
In this
Nestor
case.
Belusic is also asking, will it import 16-bit TIFF images?
Oh God, that's such a good question. And if Mia would be here, she would know that. I don't know if there's a difference for, like, I would say both, but I'm I don't.
I would guess that it does,
yeah.
but
I think it
Mia
does.
can confirm.
But Mia can confirm, yes.
Yes.
We also have we published a little thing in Microscopy today. The answer might be in there too.
Excellent. Okay, thank you, Annette.
Okay.
All right, we're going to move on to the next presentation. Let's see. Our next speaker is Hendrix Demers. He's a researcher at Hydro-Quebec, and he works on lithium battery material characterization. And before that, he was a research associate in material engineering department at McGill University, where he got his PhD. And he's been involved in the development of new methods for quantitative X-ray microanalysis, as well as data and image analysis. And today he's going to talk about a few programs he's been involved with respect to Monte Carlo simulations of X-rays and electron beam instrumentation.
Thank you, Ed. Let me share my screen. Yes. There we go. Pointer. So basically today I'm going to talk about a little bit these three programs. I'm going to do an overview of each capability of each of the program. And also I will give you a demonstration of Casino, which is something that is more useful for the community right there. So a little bit of history, a little bit about this molecular program, which basically they're all developed in Quebec in Canada. And it starts with Professor Gauvin PhD thesis, where he started writing photon molecular code to do his PhD thesis. Later, with two of his PhD students, they developed a Casino program, which was only a DOS and Unix version. Later, they kind of split in two. One of the students, Dominique Drouin, developed Casino-II with a graphical interface that we know well, and you can use on Windows. It's very useful. And more or less during the same time, when I was doing my master thesis, I developed a similar program called WinXRay. Later, Professor Gauvin, now at the University of Sherbrooke, developed the 3D version of Casino. So version 3, which is very powerful to handle 3D sample. The only sad part about Casino 3 is doesn't handle anymore the X-ray. So the X-ray simulation are not included. So I'm not going to talk too much about that today. And later, Professor Gauvin, again with a master student, continue WinXRay to develop again a 3D geometry and including the X-ray spectrum inside the calculation of motor simulation. And lately, I think it was a couple of years ago, the M6 program or code are included in Dragonfly, which is a very nice 3D reconstruction and analysis software for image and data. Just to see an overview of all the people involved in this program, you see with Casino, you were starting Professor Gauvin, Dominique Drouin, and Pierre Ovington, and after that, a couple of students that developed the 3D version and finished with the 3D version. WinXRay was me and Professor Gauvin, and M6 was Pierre Michaud, Professor Gauvin, and me later. I finished a little bit, improve a little bit the program. Nicholas already mentioned a little bit about what is multi-color simulation. Basically, we use random number to simulate the trajectory of electron inside the material and the interaction inside the material. These three programs basically use similar model, similar also that the one used by DTSA-II, and some of them define only bulk geometry or other a little bit more complex geometry. And all the data are collected from the trajectory or calculated from the trajectory. What is a little bit interesting about this program, and it's the way they calculate the X-ray. So basically, between each collision, we calculate the elastic collision, the angle, the distance. And from there, we calculate the energy loss between the two elastic collisions. And also what we do is we calculate the probability of generation of X-ray between the two elastic collisions. So it's not like Penelope that calculate each interaction of the electron to generate X-ray. In that case, we calculate the probability between elastic collisions. So it's a way faster. And in most cases, it's also relatively accurate with similar accuracy. Just to give you a better idea how we calculate the X-ray and what information we retrieve from that, basically, so from the electron trajectory, we calculate the X-ray generation, so the generation of X-ray between collision. We also include after that the emission. So basically, when the X-ray goes from the where it's generated toward the X-ray detector, the absorption by the sample. And we can also include the effect of the detector. So solid angle, the electron, the detection efficiency of the detector. So all of these are more or less included on all of these programs. And also we can see that to calculate the frequency curve, which is very useful for quantification, is basically you sum all the X-ray contribution for all electron trajectory during the simulation to create the frequency curve. I just want to point out a little bit about the terminology used. So, and actually it was well used by Nicholas Ritchie and John Donovan. So basically, when we calculate the frequency or define the frequency, we always talk about the generated one. So basically, how the X-ray generated inside the sample without taking account the absorption of the sample. And what we call emitted X-ray or frequency is basically when we take account the absorption inside the sample. In Casino, the definition is a little bit different. So we talk about non-absorbed X-ray and absorbed X-ray. So non-absorbed X-ray are the generated one, and the absorbed X-ray is what we call emitted X-ray. Now, just to give you some guideline how to download and install this software, and basically they are very similar to what the BadgerFilm installation. Basically, you go to these two websites to download either MCXray or WinXRay or Casino version 1, 2, or 3. You just download the file, you unzip the file. If you want, you can move it to another folder to copy out the file and folder. It's very important. If some file are missing, you're going to get problem with the simulation. And if you want to start a program, most of them have two versions. One is without extension too much. It's just for the old version of Windows, 32-bit Windows. And the one with _64 is for Windows 64-bit, so more modern Windows and computer. And it's way faster than 34-bit Windows. And after that, if you want, you can create a shortcut on the desktop or pin in the taskbar. Something important, because most of these programs have a command file that are very similar, but don't mix the file from this software because they are not exactly the same format, and they create a problem with the simulation, and the program will not run correctly. Okay. So the first application of this software is more like education or learning about microscopy or SCM, EPMA, and EDS. Basically, you can see the effect of accelerating voltage on the electron trajectory, the interaction volume, and you can also understand when you tilt the sample, what is going to happen. When you have different material, the effect of the interaction volume and the X-ray intensity. So it's more like educational tool, and we use it a lot when we do the SCM course at the McGill University. So that's the first application, is just educational tool. The other one is a little bit like Nicholas Ritchie mentioned, is basically to help you or guide you when you do the experiment. In that example there, this is different accelerating voltage, and we get the intensity generated for different elements. And that helps you to basically maximize your intensity at which voltage you're going to get at the maximum intensity. And you can combine that with the X-ray range to have the interaction volume and decide which voltage you want to use. So that's one application, is basically to help you do the experiment. Now the next application, and it's very interesting, is basically, this is experimental acquisition of gold nanoparticle on a thin carbon film. And it was very small, it's a couple of nanometers size gold nanoparticle. And what happened is, what we see on the carbon map is we have more carbon apparently on the gold particle, which is a little bit strange. And if you extract the spectrum, you really see that, because you really see the increase of carbon. But if you use multi-color simulation, you can understand that what happened is, because the low voltage we use, it was 5 keV. When you're on the thin carbon film, your frequency curve is almost 1. So basically, we have not a lot of emission of X-ray. But when the beam is on the gold particle, you increase your interaction volume. So this is what we see there with the multicolor simulation. And as in that case, and you lost energy in the gold particle, so you're going to generate more X-ray inside the carbon film when you're under a gold nanoparticle. And basically, the multicolor simulation helps us to understand the experimental data that we get. So this is another kind of use of the multicolor simulation. And the last example I want to do is similar to what Aurelien has presented with the BadgerFilm. You can use multicolor simulation to basically calculate, in that case, the mass absorption coefficient. And basically, you can use the multicolor simulation, compare also with the PAP and XPP program, and basically calculate the mass absorption coefficient of your experimental data. So basically, it's more like a research tool. And also, and this is what I've done a lot in the past, is just use the Monte Carlo simulation to explain different phenomena on the microscopy and X-ray microanalysis. And the last example that some students at McGill have done in the last couple of years or 10 years now is and use Monte Carlo simulation of X-ray with the F-ratio method of quantification to do experimental quantification. So basically, quickly, the way it works is we simulate a calibration curve, basically of the weight fraction versus the F-ratio using Monte Carlo. And from the calculated experimental F fraction, we can get the composition. And you can exploit that for a ternary alloy like we have there. And basically you see when we compare with K-ratio calculation, we get very similar result with this method. In that case, we only use Monte Carlo to simulate this calibration curve. And what we do is we use one experimental data to scale the Monte Carlo simulation to validate the Monte Carlo simulation, but the rest of the data is by Monte Carlo simulation. Now, a quick overview of WinXRay that I developed with Professor Owen during my master thesis. And it's quick, an old program is still working on Windows 10 and 11. I tested yesterday. And the main difference between that program and the Casino program is we add the X-ray spectrum with the background. And also, there was a very naive model of non-conductive specimen that I used during my master thesis. So that was the main contribution of that program, still available today. It's useful to get a quick X-ray spectra, but even now, I think you're better to use the DTSA-II for that. But so it's still available, but not in development anymore. Next, the next generation with the continuation of WinXRay was the MCX3. And the main contribution of that program was really a 3D sample and complex geometry that was possible. There was more imaging detector that was added, and also 3D calculation. And what was interesting for X-ray is, again, we include the X-ray spectrum, but also the X-ray mapping. So it's possible to have complex geometry and get X-ray map from that. So it's very useful for that. The interface is a little bit difficult to use, but it's very useful if you want to do X-ray mapping. Now, the main program that we're going to talk today is Casino version 2. Like I mentioned, it's very useful to do educational, so see the 3D or the electron trajectory interaction volume. And they have a couple of fixed geometry, so ball, multi-layer, grain boundary. And you can add a lot of layer as you want. And it calculates basically the characteristic X-ray and the basket-ray electron. And for the X-ray calculation, you get the result in the X-ray tab. It's only give you information about the KLM family, but it use the K alpha and L alpha and stuff like that to do the emitted intensity. And again, I already mentioned basically the definition in Casino. The non-absorbed is generated intensity and absorbed intensity is emitted intensity. Quickly, just because it's still a good program, the Casino 3 version is similar to you have a very complex 3D sample. What they add also is you can have scan point and shot noise, so very simulated to gun and to do imaging, do image simulation. And it was extended to do transmission, electron imaging on energy also, but without the diffraction. The reason important is only for amorphous sample. And also there was adding the single electron simulation. Something is very important, and this is a very important trait, is how you define your geometry for 3D sample. And this is applied for Casino 3 and MCX3. Basically, in this example, so this is two kinds of plane of the shape that touching or not touching, so the red and the blue. So basically, A is good because the electron go through the layers or the shape and the plane of the shape. So basically, it can detect easily the change of region, which is basically the change of the material. In the case of B, because the overlap of blue and red, the software itself, I have no way to know if we are in gold or copper when you go through that layer, because the superposition of the two layers. And the same thing, when you have a cross of the two layers, the definition is not clear, so that could create problem. The best way to solve this problem, and it's a little bit tricky at the beginning because the 3D geometry is a little bit difficult. My trick is to write down all my dimension on a software, on a paper or a software like a Wattpad or Notepad to see out the dimension, and add a space between a very small space, 1 angstrom. The 1 angstrom is not going to affect the result of the simulation, but allow to basically separate out the shape correctly. And also, this is more for Casino. Basically, you can define a plane with a fixed length or width. And if the width is too small, some electron or X-ray will going to go out and not be detected as a change of region. So this is a little bit tricky to get right at the beginning. And my trick also is when you define a complex 3D sample, start with a very small number of electrons to just see if the simulation makes sense are looking at the electron trajectory. And that way, you will be sure that your simulation is correct. So now the tricky part is try to do a live demo with Casino. Okay, exit. First, I need to tell you, I discovered yesterday that I have some problem with Casino and Windows 11. That doesn't happen with Windows 10, just Windows 11, and it's probably something maybe related to my screen size. So I need to check, but for some reason, Windows Casino 3 doesn't have the problem. So what I'm going to do, this is the interface that you see when you open Casino version 2. And at the beginning, the easy way to do the simulation is just click on the new button, or it could be in the file, new, and you're going to go through all the information or the option you can use step by step. So basically, when you start, you have no sample, no layers. So this is the first step where you can choose if you want a multi-layers sample or a grain boundary. So let's say I add 2 layers. And let's say, so I'll go too fast. So I add 2 layers. So because I click use substrate, the last one is a substrate with infinite thickness, and I can change the thickness of the first one in nanometers, so maybe 20 nanometers. If I want to just use thin film or thin multi-layer, I can just uncheck the substrate, and now I can specify the thickness. So let's double click on the name or the empty name and add composition. So I can just put the element symbol, and you're going to add it to the list. If I can add more element if I want, I'm going to show you for the next layer, and you can specify the density. So basically, by default, you use a table to get the density of each element or calculate the density of different components when you have more than one element. But you can use your own density or define your weight fraction and atomic fraction. So let's go give you an example for the second layers. And this is a completely random sample. So if you add your atomic fraction or atomic number of atoms, Casino calculates directly the atomic fraction and weight fraction. If you want to work with weight fraction, let's say you know that your weight fraction is 0.3 and not 0.35. Now you have to be careful, and I just saw a new bug, that you need to also change the second element or the rest of the element. Is not going to do it for you, to be sure that you have the total of 1 at the end. If you don't have total of the 1 at the end, it's not going to let you continue. So that's something that's often trick people, even me sometimes. So now we have defined your 2 layers for the multi-layer. It's similar for the grain boundary. Now, when you use grain boundary, it's not thickness, but it's a position of the layer in vertical position. So if you click next, now we're going to be able to change the setting for the simulation. So the accelerating voltage. with CalcZAF-II, what we can do also is simulate multi-energy. So not just one energy, but we can do a start and end energy and the step and simulate all of them one after each other. You can change the number of electrons. So at the beginning, 10,000 is very good because it's quick. But when you want to have more precise result, what you can do is go to, let's say, 1 million. I've done sometimes simulation with 1 billion electron, depending on the result you want to do. You can change the tilt of the sample, so the tilt angle of the sample and the beam radius. Something else is more useful when you have a grain boundary is you can scan laterally the simulation to generate at different point the simulation. And after that, you have different parameters for different distributions. So I don't think it's useful anymore to disable them, but sometimes if you have a lot of simulation and you want to save space, you can disable them. You can also change the scale, like on log scale, and also the range. You can have the distribution of energy, and I can also select if you have generated X-ray or not, again, to save a little bit of time. And you have a basically CalcZAF calculate the range automatically with simulation. You can use model also for that. Next, you have what we're going to display. So it's very interesting to display on the screen to see the trajectory. You can save a backup also, and the minimum energy of the simulation. And if you're a little bit more interested in a different model, you can change the model we use. This is the best model that we say is the for default is good, but you can change them. For example, if you want to test different model and the effect of the simulation. And you finish, and it's going to tell you if you want to start. So we're going to start. What you see, basically, you see the electron trajectory that appear, and on my computer, it's very fast. It's already done. Oops. Go back. So it's very fast for 10,000 electron. And basically, what you have is the carbon layer output and the metallic layer. And you see the different trajectory. And if you go to X-ray, basically you can see the frequency curve. And again, there's some bug in the display depending on my screen resolution, but basically, let's see if I can get it right. No. And you can also compare with the carbon one, which is basically just a thin layer at the top, and the magnesium one. Almost done. So I will just go back. So this is a quick overview of how to simulate with CalcZAF. If I go back to my presentation, there's something interesting I want to share with you. It's a little bit more advanced, but it could be useful. So basically, all this program I show you, and more of them also with another code, is basically they can be scripted or controlled by Python. And basically, you have all this package on GitHub that control CalcZAF, MCX-ray, and WinXRay. And basically, to give you some information, the script is a little bit longer, but all this function there in Python basically simulate basically the cross section or the BSC for energy between 0.1 keV to 30 keV for all elements of the periodic table and for different model implemented in CalcZAF. And that script basically run everything, create the simulation file, run them in batch, and basically do the analysis and extract the data and do the analysis and plot, on my case, plot the figure that I wanted. So this is very powerful if you want to do a lot of simulation, and but it's more for advanced people. So this is available on GitHub. And also Philippe Pinard, I have to go quickly, I have another project that tried to do the same thing, but basically have a common interface for all these programs, including Penelope, DTSA, with a graphical interface, but also a scripting interface. So let's go to the question.
Yeah. I just wanted to say thank you, Hendrix, for the talk. I particularly appreciate getting the historical genealogy for the family of Quebec developed programs. The first question was regarding what's the unit of the beam radius?
It's, I think, nanometers. It should be right down, but it's nanometers. Sorry. Yeah. And yeah, Joe have a good comment. I know I have to play, but the thing is, I have to. Let's start again. I did have to play with my
The comment is
screen resolution
regarding,
to be able. I know it's a bug, and I never be able to figure out how to solve that thing. Let's try. I think by default it should be okay.
do you want to share your screen again?
Oh yeah, sorry, I did. Yeah, there's a bug with the. So you see, if I don't change the size of the window, everything is fine. I think actually, if I have a problem, what I can do in display, you can change it to the line somewhere or point. So we see now with point, it's not very useful. You're not going to see well on your screen, but you can also have line. You see now line is okay. So we can change in the display. So again, I did not go through all the options. You have different things you can change for the display to change basically the way it shows. And maybe the last comment also, and did not talk about, but you can also export. You should just copy the display. So what is the display there, or the data itself, or export the data or the display, which is useful later when you do more than one simulation and you want to do your analysis of the result.
Okay. Thank you. One final question regarding Casino, as far as I know, is the only Monte Carlo program to simulate cathodoluminescence. Is there anything you want to say about that before we finish up?
I think if you want to do a CL, you should use Casino-III. We have developed a lot of the energy deposition that we use for CL is really well developed. You can basically have a 3D matrix, have a diffusion matrix, and I have a paper that I write down with Casino that use these for CL simulation. Yeah.
Okay, thanks very much, Hendrix.
Mm-hmm.
Okay, so our final presentation today, we're going to bring back John Donovan, and he's going to speak to us about PictureSnapApp, an application for calibration, annotation, and navigation of sample images from any source on any instrument with an XYZ or XY stage translation.
Thanks, Ed. Yeah, so this is a little bit different than what we've been seeing today, but this was actually a request by a student, grad student at Oregon, and she wanted to be able to do the same kinds of annotation and documentation that she had in some of our Pro-Free PMA software, but also on the SEM. And so I basically spent a few months and wrote this up, and I think it's actually pretty useful. You be the judge of that. But anyway, so the program is a separate download. It's right here. It's PictureSnapApp, and when you run it, you basically get a large blank window. Software is designed, I should say, to deal with not just the problem of annotating or documenting on a single instrument, your fields of view or points of interest or all that stuff, but more importantly, actually, what it really does is it also allows you to take your annotations and points of interest from one instrument to another instrument to another instrument to another instrument. And even if those instruments have different stage coordinates, if they have different orientations and different capabilities, it's kind of surprising. And there's several modes you can run the software in. And so I'll start by I'll just also mention that you can also get the information here about the software, but if you go onto the web, there's a board, PictureSnapApp board on the forum, user forum, the Pro Software user forum, and that's actually where you can get a nice tutorial and some other information. But to start out with, you would install the software, and before you open a file, you go to stage configuration. And basically, there's a demonstration mode, which kind of simulates as though you were actually talking to an instrument. And there's also this text input mode. Now, the text input mode and the demonstration modes are free. And the text input mode is used by lots of people on instruments like ICP-MS, laser ablation ICP-MS, SIMS, even TEMs. You can use it on Hitachi instruments that we don't actually directly support. There is a small charge that for if you want to get the drivers to connect to these various instruments here. I'm not exactly sure of the status of the FEI DCOM because I know that Windows has locked down a lot of that stuff. I mean, sorry, Microsoft has locked down a lot of that stuff. But the Joel stuff and the Kamika stuff for sure works. Anyway, I'm going to do this tutorial in demonstration mode just because it's easy. But the text input, the only difference with the text input mode is that instead of reading the current mag from your instrument automatically and the stage position, you actually have to indicate the field of view manually and the stage position by typing it in. But otherwise, it's exactly the same kind of functionality. And it supports 3 types of stages. And you may think this is crazy, but Cartesian stages are kind of most instruments in the world are Cartesian, and that would apply to Kamika instruments, FEI instruments. I think most SEMs are using Cartesian coordinate systems, which means that your maximum XY is in your upper right. The anti-Cartesian system is used by JEOL only, so far as I know, and that is the maximum XY is in the lower left. There's a historical reason for that, and if you see me at M&M in July and August, you can ask me about that. It's a good discussion over a beer. The half Cartesian mode is you have Cartesian in X, but your maximum, but in your Y-axis is anti-Cartesian, and that's common with any instrument that has a petrographic microscope as the imaging instrument. And so that would apply to laser ablation, ICP-MS, and other types of instruments like that. And then you can define 3 different types of units: microns, millimeters, or nanometers. And you give your stage limits. It's only if you really want to see your stage limits. Otherwise, you can just keep them to some arbitrarily large value. And then importantly, you want to indicate your horizontal field of view at 100x. And this is in the x-axis. And if you have a version of PictureSnapApp that says 9 millimeters here for Joel, that's a typo. I uploaded a version a couple weeks ago, and I meant to type 0.9, but it actually came out as 9. And I fixed that, and I just said, let's make it 1. But those are just to kind of give you, these are just rough numbers. Every instrument is slightly different, but these will get you in the ballpark. My FEI instrument, for example, the horizontal field of view at 100x is 1.49 millimeters. And then the aspect ratio, this is the shape of the image. And normally for FEI, it's this weird number here. I don't know why they chose that. Joel, it's usually 1, but it might be 4:3. And in Kamika, it's always 4:3, which is 1.333. So once you choose this, and then the instructions are here, it's very simple. I'll show you an example here. So let's open up an image, and it'll put you into this user data folder as usual, and then you go to, like, say, FEI instruments, and I'll just choose maybe this one here. Because I'm in millimeter units, it opens it up in millimeters. It doesn't have to do any transformation. And then you can see this sample holder here gives you and so the main window is always a 1-to-1 pixel mapping, and it can handle almost any size images. I think it'll handle up to 32,000 by 32,000 pixels. So some very large images can be loaded here. And of course, you can scroll to see the whole thing, but there's also a full view there. You can also resize if you need to. And then you basically, this is the blue there. If you can see that blue there, it's your field of view, current field of view. And if you'll notice in this image, it's slightly tilted. And that's because the stage is slightly rotated from orthogonal. And the software can tell that. And the reason it can tell that is if I go to this window menu here, and I click calibrate to stage coordinates, this is already calibrated image. And you'll notice it's calibrated with 3 points. If you calibrate to 3 points, you can actually detect rotation in your imaging. And that's actually a really cool thing. So basically, the way you do it is you start out with a 2-point calibration. You just pick any 2 points on your instrument that you can see in the image, and also in the actual instrument itself. And I should point out that this here actually is I think this is a camera. This is a camera picture. You can also do a flatbed scanner image. It could be a backscatter image. It could be an X-ray map. It could be any type of image that you want to import. And right now we only support, I think, JPEG, GIF, and BMP. But you can convert those, of course, and import them in. The idea, though, is you go to a location, and you can just by double-clicking on the image, and then you can adjust your field of view. In the demonstration and the text input mode, you have to use the up or down arrow keys, your cursor keys, and you can change the size of the image, and then you hold the shift key down, and you can make a smaller change. And when you're at where you think you want to be, you can, I'll close this up here, you can actually define a field of view. So you can do that with a point. You can either right click and enter some text in, and it will put that text wherever you clicked. So if I type in gobbledygook, then it's going to put that right where I right clicked. If I want to be at the spot where I actually am, you can do a shift P, I think, and then you type in some more gobbledygook, and then that's going to be at current point there. If you want to do a field of view, you go to your field of view, and then you type in shift F for field of view, and then you also type in some more gobbledygook. And so that documents your fields of view and your points. And then when you take this to another instrument, those points and fields of view actually get automatically converted. Even if you have going from Cartesian to anti-Cartesian or half Cartesian, it automatically handles that. You can transform these things manually yourself, but it does it for you automatically if you want. So to move on, I'm going to close this image, and I'm going to open up another image, and this will be an image that is that was from my Kamika instrument. And let's see, where is that? Here it is. And I think I just opened this one up here. Okay, so, okay, that's a good point. So I forgot to change the units from millimeters to microns, because the Kamika is in micron stage units, but it automatically did it for me. And so now everything now is going to be in micron units. This was not the picture I wanted. Let me close this and open up the one that's in my list here. I think it's this one here. I transformed it again into millimeters. And this was a cross polars scan of a thin section. And so here's the whole thin section right here. I can double click on this small image, and it will take me at my field of view to this place here. I can adjust my field of view depending on what the instrument actually is at. And let's see. Yeah, there you go. And I can load in an image into this thing by using this image locator feature. But I'm going to show you how this works. So what this is doing is showing me the images that I've already loaded in. And you'll notice, you see this crack right here. You can see that this backscatter image on top of this optical image actually corresponds to that. I can click on another, I can double click on another image, and it will drive to that point there. And here you can see these cracks here. So this is, these images are now all calibrated, and you get an exact location. I can choose to, you can also get a distance measurement by dragging your mouse. So you can get the distance of anything if you want in your stage units. And so the way you do this is you go to the area, you go to the spot where your image is. If you're connected to the instrument live, you can, the field of view will automatically be sized correctly. If you're not in that mode, you can use, again, the up and down arrow keys to adjust the image size, and then you can select a remote image. And this means usually that you've, on some other software, and it could be Pro for EPMA, it could be Joel, Kamika, whatever, FEI, you browse to that image, and you select it. And as long as you haven't changed the mag or the stage position, then it knows where that is. based on this current field of view, and it will load that into that window there. So that ends up being pretty cool. And then you can obviously remove images. You can export your coordinates. You can add an image that's already calibrated. So if the image is already calibrated, you can add that to the list. A calibrated image would mean an image that contains stage coordinates and field of view information. And that would apply, as Annette mentioned, in the reimager software to any file that has an ACQ file attached to it. And so the reimager will use the ACQ file information for the stage calibration to size your image properly. And let's see. Oh, I should also mention on this calibration thing here. I mentioned that you start out with 2 points on a diagonal. You want to pick something, any 2 points on a diagonal, because the diagonal will give you the X and Y calibration. But once you've got that X and Y calibration, and the image is clickable, I mean, as you can move your current position to that point, you want to pick a third point. And the third point could either be anywhere perpendicular to that diagonal, ideally. And when you get the third point, but move to that spot first before you change modes, because once you change modes, the image won't be calibrated until you click Calibrate Image again. And then in this case of this image, you can display the calibration points. And if I go to, let's see, if you go here, I'll close this window here and close that window there. The calibration points, you can see there's a grain here she calibrated on, a grain here she calibrated on. Can everyone see that? Yeah, there's a number 1 calibration point, number 2 calibration point, and then she picked the number 3 calibration point. So the student was picked 3 points that she could find that roughly form a triangle. The idea, again, being that points 1 and 2 are on a diagonal, and the third point is somewhere else. It could be here, it could be over there, as long as it creates a stress in terms of the X and Y calibration. And that will then handle imaging that is rotated slightly or even a lot. Let's see. And then, okay, and here's a gobbledygook. I just typed that in for fun. Field of view here, but yeah, there's the first calibration point. So, and then you can also list all your annotations, which we have none. So if I right click and I say test annotation, I can do that. And now I have a test annotation on that spot there. And you can see now my test annotation is here. These can be exported. You can move to that position, anything you want to do. And then how am I doing for time? It's a couple minutes. Okay, let me show you one more thing.
I think we're gonna wrap it up if you can.
I'll show one more fun thing.
All right.
Just really quick. You can also use this to document standards. So I have here a standard mount. And if I pick, like, I think I pick this one here, and again, it's going to convert it to millimeters because I forgot to. This is one of my standard mounts, and those are the 3 positions I used to calibrate it. And if I go to my image locator, I can actually display backscatter images on this, or even all the images. Let's see, display all image locations. So that's it, Ed. I'll let that pop up while it runs. There you go.
That's
so now
excellent. Thank you, John. That's a real fantastic time saver. And I think it's really excellent for having confidence regarding your image registration when you're moving between imaging systems, or you're moving to a higher sensitivity measurement system. Maybe you're going to the synchrotron or whatever.
I mean, I have so many people that tell me that this saved their butts, you know, when they were going, you know, from their laser ablation to their microprobe or microprobe to laser ablation. It really allows them to have confidence they can relocate things. I notice in some sims, it's pretty hard to know where you are sometimes. So that's another. You want to make sure, though, that you want to have your calibration points visible in the multiple techniques. So whether it's optical or some kind of electron imaging, you want to make sure you choose points that can be found. So, and that could mean even scribing little points on your sample.
Well, thank you, John. You gave 2 talks today, and we really appreciate your taking time out, as well as all the speakers we heard from today. Everybody who does microanalysis spends a lot of time with their primary systems, and no matter how capable they are, we all need to go to third-party solutions sometime. And we heard about a number of them today, and beautifully, they're all available at no cost. So I want to thank the Microanalysis Society for sponsoring the event. And sometime soon, this video will be not edited, but posted up, maybe compressed before it's posted online for you to view. And I would like to thank everyone who attended today for tuning in. Thanks very much.